Tonight, step outside with me for just a moment. Not in your mind yet. Just feel the window, on the other side of that glass. The sun has been burning all day, 93 million miles away, pouring more energy onto your roof in a single afternoon than your home could use in a year. And yet, just beyond the thin skin of air above you, space sits at nearly 450 degrees below 0 Fahrenheit. Colder than anything you will ever touch. Colder than the darkest freezer ever built. The sun is there. Its fire is real. And the cold is equally real. 9 minutes of light. Travel away. That contradiction. The fire and the freeze existing together, separated by almost nothing, is one of the most quietly beautiful puzzles in physics. Tonight, we walk through it slowly. No rush, no pressure to remember anything. Just the story of why heat and cold can share the same sky. There is a particular kind of question that arrives without warning. It does not come from a textbook. It does not arrive after years of study or careful preparation. It arrives the way most honest questions do, in the middle of something ordinary, when the mind is relaxed enough to notice what it has been taking for granted. Maybe it happens on an airplane. You are somewhere above the clouds, watching the sun pour gold across an endless white floor below you, and the window beside your seat is cold enough to make your fingertips ache. You press your palm flat against the glass and hold it there, feeling the chill move into your hand. And somewhere in the quiet part of your mind, a thought surfaces, slow and unhurried. The sun is right there. I can see it. I can feel its light on my face through this very window. So why is the glass so cold? Or maybe it happens to a child in a backyard on a summer afternoon. The sun is blazing. The concrete is hot enough to burn bare feet. And the child looks up, squinting into the brightness, and asks the adult nearby the most reasonable question in the world. If the sun is that hot, why is space cold? The adult smiles and says something about distance. Something about how the farther you get from a fire, the cooler it becomes. The child nods, but something does not quite settle, because you can still feel a campfire from 50 feet away. You can still feel the warmth of a fireplace from across a room. So why does the sun, a fire so enormous it could swallow 1,000,000 Earths, fail to warm the space just above the sky? The adult does not have the full answer. Almost no adult does, because the full answer turns out to be one of the most surprising things in all of physics. And it is the kind of surprise that, once you truly understand it, changes the way you look at heat, at cold, at the sun, and at the thin layer of air that stands between you and the void every moment of your life. Here is what makes the question so deceptive. It feels like it should be simple. Distance, we assume, is the explanation. Heat weakens with distance the way a shout fades as you walk away from it. So surely space is cold simply because the sun is far away. That explanation is not wrong. Exactly. Distance does play a role, and we will follow that thread carefully later tonight. But distance alone does not come close to explaining what is actually happening. If distance were the whole story, the space just above our atmosphere, which is barely a scratch on the surface of the distance between us and the sun, should still be warm. After all, we are essentially sitting on the sun's doorstep, cosmically speaking, and yet the temperature just beyond our atmosphere plunges toward a cold so severe it has no equivalent anywhere in ordinary human life. So something else is happening. Something that has nothing to do with how far you are from the fire, and everything to do with what sits between you and it. To find that something, we have to go back, not all the way to the beginning of the universe. Not yet. Just back to the centuries when human beings first began asking what heat actually is. Because it turns out that for most of recorded history, The smartest people in the world had the wrong answer. Not a slightly wrong answer. A completely, confidently, elegantly wrong answer. And the story of how that wrong answer was replaced by the right one is one of the quietest revolutions in the history of science. For most of the 1700s and 1800s, educated people believed that heat was a substance, a real, physical thing, like water or air, that flowed from one place to another and accumulated inside objects the way water fills a cup. They gave this substance a name. They called it caloric. The idea was elegant in the way that wrong ideas often are. When you held a hot iron near your skin and felt the warmth, caloric was flowing from the iron into the air around it, and then into you. When ice melted in your hand, caloric from your warm skin was flowing into the cold ice, releasing it as it went. Hot things had a lot of caloric, cold things had very little. Temperature was simply a measure of how much caloric an object contained. The caloric theory explained a great many things well enough to survive for nearly 2 centuries. Chemists built careful experiments around it. Textbooks taught it as settled science. And the people who believed it were not foolish. They were working with the best tools and the best observations available to them. And caloric fit those observations reasonably well. The first serious crack appeared, quietly and unglamorously, in a cannon factory in Munich in the year 1798. A man named Benjamin Thompson, who went by the title Count Rumford, was overseeing the boring of cannon barrels when he noticed something the caloric theory could not explain. The metal got hot as it was being bored, very hot, hot enough to boil water. The caloric explanation said the boring process was releasing caloric stored inside the metal. But Rumford kept boring, and the metal kept producing heat. It produced heat continuously, seemingly without limit, as long as the boring continued. If caloric were a stored substance, it should have run out. It never did. Rumford published his observations, suggested that heat might be a form of motion rather than a substance, and was largely ignored. The caloric theory was too comfortable, too useful, and too well established to fall to one inconvenient observation from a cannon factory. It took another 50 years and the careful work of several other scientists before the true nature of heat began to come into focus. What they eventually understood changed everything. Heat is not a substance at all. It is motion, the movement of atoms and molecules, vibrating and colliding and transferring energy to everything they touch. When something is hot, its molecules are moving fast. When something is cold, they are moving slowly. Temperature is simply a measure of the average speed of that motion. And cold, true cold, is not the presence of some opposing force flowing in to replace warmth. Cold is the slowing of motion. The closer you get to absolute zero, the slower everything moves, until thermal motion approaches its lowest possible state. That single shift in understanding, from heat as substance to heat as motion, is the key that unlocks everything we will explore tonight. Because once you know that heat is motion, a question immediately arises. How does motion travel from one place to another? And the answer to that question is the answer to the question the child asked in the backyard. It is the answer that explains why space is cold even though the sun is hot. And it begins with something so familiar, so utterly everyday, that you have felt it thousands of times without ever stopping to ask why it works the way it does. It begins with the moment you place your hand on a cold window pane and feel the chill move into your fingers. That feeling, that simple transfer, is the first of 3 ways that heat moves through the world. And one of those 3 ways is so different from the others, so strange in its behavior, that it is the only one capable of crossing the void between the sun and your skin. 2 of the 3 need something to travel through. One of them needs nothing at all. We are going to meet all three tonight. And by the time we have the question the child asked, we'll have an answer. Not a simple answer, a true one, which, as you are about to discover, is considerably more interesting. For now, let your breathing slow a little. Let the day release its grip. Muscle by muscle, the question has been asked. The journey is just beginning, and the first step is understanding something so basic and so consistently overlooked that most people never think to question it. What is heat? Exactly, and where? In the enormous silence between stars. Does it go? Take a moment to feel your own hand. Not dramatically. Just rest it open on the blanket beside you and notice that it is warm. Notice the warmth without trying to explain it. It is simply there, gentle and constant, the way it always is, the way it has been your entire life. You have probably never thought of your hand as a collection of trillions of tiny objects moving at hundreds of miles per second. But that is exactly what it is. Every atom, in every molecule, of every cell, is vibrating right now, ceaselessly, in motions so small, they make the width of a human hair look like a continent. That vibration is not a side effect of being warm. That vibration is what being warm means. This is the thing the caloric theorists missed. They were looking for a substance, a fluid, something that could be poured and measured and contained. And they were wrong not because they were careless, but because the truth was so far outside the vocabulary of their time that they could not have found it by looking harder in the same direction. The truth required a completely different way of seeing matter itself. Let us build that way of seeing, slowly and without hurry, in the quiet of tonight. Everything around you right now is made of atoms. The blanket, the air, the walls, the floor beneath the floor. Atoms are almost unimaginably small. If you lined up 100 million of them in a row, they would stretch approximately 1 centimeter. A single human hair is roughly 1 million atoms wide. These are not poetic exaggerations. They are measurements, confirmed by instruments precise enough to image individual atoms directly. Instruments that exist now in laboratories around the world. Atoms almost never travel alone. They bond to other atoms to form molecules. And molecules are the basic units of most of the matter you interact with in daily life. A water molecule is 2 hydrogen atoms bonded to 1 oxygen atom. The air you are breathing right now is mostly nitrogen molecules. Each one a pair of nitrogen atoms locked together, along with oxygen molecules built the same way, and a thin scattering of other gases. Now, here is the part that changes everything. None of these molecules are sitting still. At any temperature, above absolute zero, every molecule in existence is in constant motion. In a gas, like the air filling your room, molecules move freely, flying through space and colliding with each other billions of times per second, bouncing off walls and surfaces and each other in a ceaseless, invisible dance. In a liquid, molecules slide and tumble past one another, still moving, but constrained by their neighbors. In a solid, molecules cannot move freely, but they are not still either. They vibrate in place, like a ball on a spring, oscillating back and forth around a fixed position. Faster when warm, slower when cool. Temperature is the measure of that motion. Specifically, temperature measures the average kinetic energy of the molecules in a substance, where kinetic energy is simply the energy of movement. The faster the molecules move on average, the higher the temperature, the slower they move. The lower the temperature, this means something profound that is worth sitting with before we move on. When you hold a warm cup of tea, you are not holding something that contains a mysterious heating fluid. You are holding a collection of molecules moving faster than the molecules in your hand. When those faster-moving molecules collide with the slower-moving molecules in your skin, they transfer some of their energy. Your hand's molecules speed up slightly. The cup's molecules slow down slightly. You feel warmth. The cup cools a little. What happened was not a substance flowing from one place to another. It was a redistribution of motion, a statistical evening out of energy between two populations of vibrating things. That redistribution has a name. Scientists call it thermal energy transfer. The rest of us call it heat. And the direction it flows is not arbitrary. It always, without exception, flows from faster-moving molecules to slower-moving ones. From hot to cold, never the other way around. Not spontaneously, not without work being done. That one-way direction is one of the deepest facts in all of physics. And we will come back to it later tonight when we follow it all the way to the fate of the universe itself. But first, let us follow the motion downward. Because if heat is motion, then cold is simply less motion. And the logical endpoint of less and less motion is a state where thermal motion approaches its absolute minimum. Here is where quantum mechanics enters quietly. And it matters. Even at the very floor of temperature, particles are not completely still. The laws of quantum mechanics, specifically the uncertainty principle, first described by Werner Heisenberg in the 1920s, tell us that particles cannot simultaneously have a perfectly defined position and zero momentum, even at absolute zero. A residual vibration called zero-point motion persists. It cannot be removed. It is not thermal energy in the ordinary sense. It is a fundamental quantum mechanical property of matter itself. So cold, even the most extreme cold anywhere in the universe, is not the complete absence of all motion. It is the absence of thermal motion. The random, temperature-dependent vibration that we measure and feel as warmth. The floor is real, but even at the floor, something remains. Something quantum mechanics will not permit to go silent. Physicists measure temperature on a scale that begins at that floor. It is called the Kelvin scale, named after the Scottish physicist William Thomson, later known as Lord Kelvin, who did foundational work in the 19th century on the relationship between heat and energy. On the Kelvin scale, 0 is not an arbitrary reference point, like the freezing of water or the comfort of a human body. 0 Kelvin is the absolute floor, the temperature at which thermal motion would reach its lowest possible quantum mechanical state, the coldest anything can ever be. 0 Kelvin is equal to negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. There is no lower temperature. Not in theory, not in practice, not anywhere in the universe. Ever. Here is something that gives this fact a strange beauty. We have never actually reached absolute zero. Not once. Not in any laboratory on Earth. Not anywhere in the known universe. The closest humanity has come was achieved by researchers at the Massachusetts Institute of Technology who, in the year 2021, cooled a gas of sodium atoms to approximately 38 picokelvin, 38 trillionths of a degree above absolute zero. And yet even that extraordinary achievement was not absolute zero. The third law of thermodynamics tells us that reaching it would require infinite work. The floor exists, but the floor cannot be touched. Now bring all of this back to the question we carried into tonight. Space. The deep space between planets and between stars has a background radiation temperature of approximately 2.7 Kelvin on average. That is 2.7 degrees above absolute zero. The coldest naturally occurring place on Earth, in Antarctica in the middle of winter, might reach around -90 degrees Celsius. The background of space is more than 40 times colder than that, closer to the absolute floor than to anything a human body has ever experienced. And the sun, 93 million miles away, burns at a surface temperature of approximately 5,778 degrees Celsius. Its outer atmosphere reaches temperatures of 1 to 3 million degrees Celsius. A mystery we will spend a full chapter on later tonight. So we have two temperatures, nearly 3 million degrees, and nearly zero, and between them, only 93 million miles of space. The question the child asked is not really about distance. It is about something more fundamental. It is about what sits in that space, and what that means for how energy can travel across it. And the answer begins with a question that seems almost too simple to ask. What is between the sun and you? The answer, given carefully and honestly, is almost nothing. A near-perfect vacuum, a scarcity of matter so complete that if you could somehow gather all the atoms scattered through a volume of deep space, the size of a large house, you would have less material than a single breath of air. Heat, as we now understand it, is the motion of molecules. But to transfer that motion in most of the ways we are familiar with, you need molecules to do the transferring. You need matter. You need something to vibrate, something to collide, something to carry the motion from one place to another. Space has almost none of that. So how does any energy reach us from the sun at all? How does warmth cross 93 million miles of near emptiness and land on your skin on a summer afternoon? The answer is that heat has a third way of traveling, a way that needs no molecules, no matter, no medium of any kind. A way so different from the other two that understanding it requires a small shift in how you think about what light actually is. That shift is the one that unlocks the whole puzzle. Rest here for a moment. Feel the warmth of your hand again, if you like. Trillions of tiny motions happening right now, in every cell, and somewhere above the atmosphere. An absence of those motions, so complete it borders on the philosophical. Both things are true, and between them lies one of the most beautiful mechanisms in all of physics. Hold out your hand toward an imaginary fire, not close enough to burn, just close enough to feel the warmth moving toward you across the air. Feel it on your palm, your fingers, the inside of your wrist. Notice the distance between your hand and the flame. Notice that nothing visible is crossing that gap. No wire, no string, no chain of anything you could touch. And yet, the warmth arrives, crossing the space between you and the fire as if distance were no obstacle at all. Stay with that sensation for just a moment before we name it, because this is the sensation at the heart of the child's question. Heat crossing space, energy moving from a source to a receiver without anything visibly carrying it. And the reason it can do this is the same reason the sun can warm your face from 93 million miles away. Heat travels through the universe in exactly 3 ways. Not 2, not 4, 3. And each one tells a different story about what energy is willing to do to get from one place to another. 2 of them are everywhere in your daily life. One of them is the reason you are warm right now on a planet 93 million miles from the nearest fire. The first way is the one you have felt most often, probably without ever giving it a name. Imagine reaching for a metal spoon resting in a bowl of hot soup. The moment your fingers close around the handle, you feel it. The heat moves into your hand almost immediately. You did not need to hold the spoon near the soup and wait. You did not need to wave it through warm air. You touched it, and the heat came directly to you, molecule by molecule, in a chain so immediate it felt instantaneous. This is conduction, the transfer of heat through direct physical contact. Vibration passing from one molecule to the next, like a message passed hand to hand down a long line of people. When your cooler fingers touched the hotter spoon, the faster-moving molecules in the metal collided with the slower-moving molecules in your skin. Those collisions transferred kinetic energy. Your skin's molecules sped up. The spoons slowed very slightly. The effect cascaded inward, and within moments you felt warm. Conduction is efficient when molecules are tightly packed and good at passing vibration between themselves. Metals are extraordinary conductors because their electrons move freely, carrying energy rapidly from one region to another. This is why a metal spoon in hot soup feels hot almost immediately. Wood, by contrast, conducts poorly. This is why a wooden handle on a pot stays cool even as the metal above it heats up. And it is why early humans used wood and bone rather than metal for tools they needed to hold near fire. Conduction requires direct contact. Remove the contact, break the chain, and conduction stops. Let that sit for just a second. A chain of molecules, each one passing motion to the next. Intimate, continuous, physical, and completely useless in the emptiness of space. The second way heat travels is more visible, and you encounter it every time you feel a warm breeze or watch the shimmer rising above a hot road on a summer afternoon. Heat a pot of water on a stove. The water at the bottom, nearest the burner, warms first. Its molecules speed up. As they speed up, they spread apart slightly, making the warm water less dense than the cool water above it. Less dense water rises. Cool water from above sinks to take its place. The cool water then heats up, rise, and the cycle continues. Within minutes, the entire pot is in gentle motion. A slow churning loop, driven by nothing more than the relationship between temperature, density, and gravity. This is convection. Heat transfer through the movement of a fluid, which in physics means either a liquid or a gas, both of which flow and circulate freely. The atmosphere of Earth moves heat by convection constantly. Warm air rises from sun-heated ground. Cool air rushes in to replace it. And the result is weather, wind, the circulation of the entire atmosphere. Ocean currents carry warm water from the tropics toward the poles and return cool water back. The interior of the Earth moves heat from the hot core toward the surface through slow convection in the mantle, driving the drift of continents across billions of years. Convection can move enormous amounts of energy, but it requires something to flow. It requires a medium, a substance that can be heated, that can become less dense when warm, that can rise and carry its energy with it. In empty space, there is no such medium. There is nothing to heat, nothing to become less dense, nothing to rise or sink or carry warmth from one region to another. So we have two ways of moving heat, and both of them have just failed the test. Conduction requires direct contact, and the sun is not touching you. Convection requires a flowing medium, and space has almost none. This is the moment in the story where something unexpected has to happen, and it does. The third way heat travels is not like the first two at all. It does not require matter. It does not require contact. It does not require anything to flow or vibrate or touch. It can cross a perfect vacuum as easily as it crosses a room, and it does so at the fastest speed the universe permits. The third way is radiation. To understand radiation properly, we need to take one small step into the nature of light itself. Radiation, in this context, does not mean radioactivity. It means electromagnetic radiation, which includes visible light, but extends far beyond what human eyes can see. Infrared light, which you feel as warmth on your skin. Ultraviolet light, which burns the skin on a summer day. Radio waves, microwaves, X-rays, gamma rays. All of these are the same fundamental phenomenon. Electromagnetic waves traveling through space at the speed of light, differing only in their wavelength and frequency. And here is the remarkable thing. Every object that has a temperature above absolute zero emits electromagnetic radiation. Every single one. Your body, right now, is radiating heat in the form of infrared light. You are glowing, softly, invisibly, in wavelengths your eyes cannot see, but that infrared cameras detect perfectly clearly. The walls of the room you are in are also glowing. The ground outside is glowing. The sun is glowing, brilliantly and powerfully, across a broad spectrum that includes the visible light you see and the infrared warmth you feel. Electromagnetic radiation needs no medium to travel through. It is not a vibration of matter the way sound is. It is a vibration of electric and magnetic fields, which propagate through a perfect vacuum just as readily as through air. When a photon, a single packet of electromagnetic energy, leaves the surface of the sun, it does not need molecules to carry it forward. It travels at the speed of light through empty space, and if nothing intercepts it, it will travel that way essentially forever. This is how the sun's energy reaches Earth, not by conduction. There is nothing connecting them, not by convection. There is no atmosphere between them to circulate. By radiation, pure electromagnetic radiation streaming outward in all directions, crossing 93 million miles of near vacuum in approximately 8 minutes and 20 seconds. But here is the precise and important distinction that the child's question is really about, and that most explanations skip past too quickly. The radiation itself is not heat. Not yet. A photon traveling through space carries energy, but it does not warm the vacuum it passes through, because the vacuum has almost nothing to absorb it. The photon moves through space without interacting with it, without sharing its energy, without warming it at all. Space stays cold because there is almost nothing in space to absorb the radiation and convert it into molecular motion. The warmth happens at the endpoint. When radiation is absorbed by matter, the energy of the photon is converted into kinetic energy of molecules. The matter's molecules speed up. The matter becomes warmer. The radiation becomes heat only at the moment of absorption. On Earth, the atmosphere absorbs some incoming solar radiation. The ground absorbs more. The oceans absorb enormous amounts. Every surface that faces the sun absorbs radiation and converts it into warmth. This is why you feel hot standing in direct sunlight and noticeably cooler the moment a cloud passes over. The cloud intercepts some of the radiation before it reaches you. Less radiation absorbed means less molecular motion, means less warmth. In space, above the atmosphere, the same radiation is present. The same photons are streaming past, but there is almost nothing to absorb them. The radiation passes through without transferring its energy, without warming anything, without creating the molecular motion that we measure as temperature. This is the answer to the child's question. Space is cold not because the sun's energy disappears. The energy is there, streaming through the void in every direction. Space is cold because there is almost nothing in the void to receive it. The sun does not heat space. It heats things, and space has almost none. Sit with that for a moment. Not the physics of it, just the image. 1 billion photons crossing 93 million miles of cold silence, arriving at the outer edge of Earth's atmosphere. And only then, only when they strike something willing to receive them, becoming the warmth you feel on a summer afternoon. The warmth is not in the light. It is in the meeting. It is in the moment when light finds matter and the two exchange what they have. The thin blue line of atmosphere wrapped around this planet is the place where that meeting happens for us. Above it, electromagnetic energy streams freely through space, crossing the void without warming it. Below it, That same energy converts to warmth on every surface it touches, heating the ground, stirring the air, driving the weather, making the planet the place it is. We have now laid the foundation for everything else in tonight's journey. Heat is motion. It travels in 3 ways. Only one of those ways can cross empty space. And that way does not heat the space it crosses. Let your mind rest on those ideas as gently as you can. Each chapter ahead builds on what we have just built together. Slowly, in the unhurried way that the best ideas deserve. The sun is hot. Space is cold. And now you know why both of those things can be true at the same time. There is a moment that every astronaut describes differently, but they all describe it. The moment the hatch opens, not the launch, which is violence and noise and the feeling of being pressed into a seat by invisible hands. Not the arrival in orbit, which is disorientation and wonder in equal measure. The moment the hatch opens and they float out into open space for the first time, and the universe presents itself without a window between them and it. What they describe is not cold. Not at first. What they describe is the sun. On the side of their body facing the sun, the heat is immediate and intense. Not the gentle warmth of a summer afternoon, but something closer to standing a few feet from a large open fire. The side of their helmet facing the sun can reach temperatures of approximately 250 degrees Fahrenheit if unprotected. Metal surfaces on the outside of the space station, on the sun-facing side, reach temperatures that would burn skin in an instant. And on the other side of their body, the side in shadow, the cold is equally immediate. Surfaces in shadow in space can drop to approximately negative 250 degrees Fahrenheit. The difference between the sun side and the shadow side of a single object in orbit can exceed 500 degrees Fahrenheit. Same object, same moment. 500 degrees of difference, separated by a few inches of material. Let that land before we continue. Not 500 degrees across a room. Not 500 degrees across a city. 500 degrees across the width of a spacesuit. Between the side facing a star and the side facing the dark. This single image, one astronaut floating in open space with one side blazing and one side frozen, contains the entire answer to the question we have been building toward. And it reveals something that most people, even most educated people, have never quite seen clearly. A very natural but very misleading assumption about how heat works in space. We tend to speak about space as if it has a temperature the way a room has a temperature. We say space is cold, roughly 2.7 Kelvin on average. And that is a meaningful number, but it describes something very specific. The temperature of the ancient radiation field filling the universe in every direction. It does not describe the temperature of the vacuum itself, because the vacuum does not have a temperature in the way a bowl of water or a room full of air does. There are almost no molecules in the vacuum to measure. What this means in practice is that objects in space do not simply take on the temperature of their surroundings the way objects do on Earth. On Earth, if you leave a glass of water on a table, it will eventually reach the same temperature as the room. The air molecules collide with the glass continuously, transferring energy back and forth until everything settles. This process, driven by conduction and convection, is so constant and so thorough on Earth that we take it completely for granted. In space, that process barely exists. There are almost no air molecules to collide with your surface. Conduction requires contact, and there is nothing to make contact with. Convection requires a fluid medium, and there is none. The only way energy moves to or from an object in space is through radiation. And radiation follows its own rules. Rules that depend not on the temperature of the surrounding vacuum, but on the temperature of the radiating sources and the object itself. So an object in space is not sitting in a cold environment the way an ice cube sits in a warm room. It is sitting in a radiation environment, receiving intense electromagnetic energy from one direction and radiating its own energy outward in all directions toward the dark. Its temperature settles at whatever equilibrium point balances the energy it absorbs against the energy it radiates away. For the moon, which has no atmosphere to complicate things, this balance is stark and visible. The moon is almost the same distance from the sun as Earth. It receives almost exactly the same amount of solar radiation per square meter. And yet the moon's surface swings between extremes that make Earth's most severe climates look mild. On the sun-facing side near the equator, at lunar noon, the surface temperature reaches approximately 260 degrees Fahrenheit. On the night side, temperatures drop to approximately negative 280 degrees Fahrenheit. Over the course of a lunar day, the same patch of ground swings through a temperature range of more than 500 degrees. Earth, receiving the same solar radiation, maintains a global average surface temperature of approximately 59 degrees Fahrenheit. The difference is not distance from the sun. The moon is essentially at the same distance. The difference is atmosphere. Earth's atmosphere does several things simultaneously that the moon's bare surface cannot. It scatters incoming solar radiation, distributing it more evenly. It absorbs some wavelengths before they reach the ground, moderating the intensity of direct sunlight. It holds heat near the surface through a process we will explore in its own chapter later tonight. And it moves heat around through convection, the wind and weather systems that carry warmth from the equator toward the poles and prevent any one region from becoming as extreme as the lunar surface. The moon is what Earth would be without its atmosphere. Not cold, like deep space, because the sun is still there, still sending radiation, still heating whatever surface is turned toward it, but violently variable, swinging between extremes with nothing to buffer the transitions, nothing to hold warmth through the night, nothing to share heat between the day side and the night side. Now return to the astronaut floating outside the hatch. Their spacesuit is doing what Earth's atmosphere does for the planet. But for one human body, the suit reflects a significant portion of the incoming solar radiation on the sun-facing side. It slows the radiation of heat from the shadow side, and it actively moves heat around within itself, maintaining the astronaut's body at a survivable temperature, despite the 500-degree difference surrounding them. The suit is not fighting the cold of space in the way you might fight the cold of a winter night by piling on blankets. Blankets work by slowing conduction and convection, trapping warm air close to the body. In space, there is no cold air pressing in from outside. There is no convection at all. The challenge is not keeping warmth from being conducted away. It is managing the flow of radiated energy, which follows completely different rules. This distinction matters because it reveals something about the cold of space that is easy to miss. The cold of space is not an aggressive force pushing inward. It is an absence of matter to conduct warmth away slowly, an absence of fluid to convect warmth away gently. In that absence, the only thermal process is radiation, and radiation is indifferent to your comfort. It simply carries energy from wherever it is concentrated toward wherever it is less concentrated, at the speed of light, without negotiation. A human body in space, without a suit, would not freeze in the way a person freezes in an Arctic blizzard. The cold of a blizzard is active, wind-driven convection, stripping warmth from exposed skin at a ferocious rate. In space, the primary dangers are the vacuum itself and the direct radiation of the sun. The cold would come eventually, through radiation, as the body emitted more infrared energy than it received from any source. But it would come more slowly than most people imagine, because radiation is a slower way to lose heat than conduction or convection. What all of this points toward is a simple but counterintuitive truth. Space is not cold the way a refrigerator is cold. A refrigerator is cold because it actively removes heat from its interior, and the air inside conducts that coldness to everything stored there. Space is cold because it is empty, and emptiness means that radiation, the only remaining mechanism, spreads energy so thinly across such enormous distances that objects with no internal heat source drift gradually toward the temperature of the ancient radiation background that fills the universe on average. That background, approximately 2.7 Kelvin on average, is the coldest the universe currently gets across most of its volume, not because something is actively removing heat, but because the universe has been expanding for 13.8 billion years, and the ancient light filling it has cooled almost to nothing. Almost nothing, but not quite nothing, because that 2.7 Kelvin on average is not an arbitrary number. It is a message from the beginning of time, still traveling, still filling every corner of space in every direction, carrying within it the history of everything that happened in the first moments of existence. To understand that message, we need to go somewhere we have not been yet tonight. We need to go back to a moment when the universe was not cold at all, when it was the hottest thing that has ever existed, when all the light we will ever see was set free in a single ancient clearing. Let your breathing settle for a moment. Let the image of the astronaut in the hatch stay with you. One side warm, one side cold. The whole universe demonstrating its rules on one small human form floating in silence. We go further back now, much further back, to the moment the light was first set free. Feel the air on your skin for a moment. Not dramatically. Just notice it. The faint pressure of it. The almost imperceptible sensation of being in contact with something, even though air is nearly invisible and seems like almost nothing at all. Notice how the air carries the temperature of the room. Notice how you know, without touching anything, approximately how warm or cool this moment is, simply by being present in it. Now imagine that even that, almost nothing, is taken away. Not the air in the room, the air everywhere, the molecules between the planets, the particles drifting between the stars. Imagine a region of space so empty that a cubic centimeter of it contains only a handful of atoms, compared to the 27 billion atoms in every cubic centimeter of the air you are breathing right now. Imagine a silence so complete, and a vacancy so thorough, that the concept of temperature itself begins to blur at the edges. What temperature would it be? In that almost nothing, the question sounds like philosophy. It turns out to be physics, and the answer is one of the most remarkable numbers in all of science. Before we arrive at the number, we need to stay with the question a little longer, because asking for the temperature of empty space runs immediately into a problem we built in the earlier chapters. Temperature is a measure of the average kinetic energy of molecules. It is a property of matter in motion. Empty space has almost no matter. So in what sense can it have a temperature at all? The answer requires a small expansion of what temperature means. When physicists speak of the temperature of the vacuum of space, they are not talking about the motion of molecules, because there are almost none. They are talking about the radiation field, the electromagnetic energy that fills the space, the photons traveling in every direction, carrying energy from every source that has ever emitted light. The temperature of that radiation field is defined by the intensity and wavelength distribution of the photons within it. And it turns out to be a perfectly meaningful and measurable quantity. And the value of that quantity, measured carefully in every direction anyone has ever looked, is approximately 2.7 Kelvin on average. Everywhere, in every direction. Whether you point your instruments toward the center of our galaxy or toward the empty space between galaxy clusters, Whether you look toward the sun or directly away from it, the background radiation field of the universe has the same temperature to extraordinary precision. Not roughly the same to within tiny fractions of a degree that required the most sensitive instruments humanity has ever built to detect. This uniformity is one of the strangest and most beautiful facts about the universe, and it demands an explanation. The answer takes us back in time, further than most of us ever think to go. 13.8 billion years ago, the universe began in a state of almost unimaginable density and temperature. Space itself began to expand, carrying everything in it outward. And as it expanded, it cooled. This is a fundamental relationship in cosmology. When space expands, the radiation within it stretches. Stretched radiation has longer wavelengths. Longer wavelengths mean lower energy. Lower energy means lower temperature. As the universe grew larger, its temperature fell. In the first fractions of a second, the temperature was trillions of degrees. Within a few minutes, it had fallen to hundreds of millions of degrees, cool enough for protons and neutrons to begin forming atomic nuclei. For the next 380,000 years, the universe was a hot, dense fog, opaque to light, a plasma of charged particles so tightly packed that photons could not travel freely. They were continuously absorbed and re-emitted, trapped in the glowing plasma like light inside frosted glass. Then, 380,000 years after the beginning, something changed. The universe cooled to approximately 3,000 degrees Kelvin, cool enough for electrons to combine with atomic nuclei and form neutral atoms for the first time. And in that moment, the fog cleared. The photons that had been trapped in the plasma were suddenly free. They streamed outward in every direction. The first light to travel unimpeded through the universe, filling all of space with a brilliant, ancient glow. And then the universe kept expanding. Over the next 13.8 billion years, that ancient light stretched with the expanding space. Its wavelengths grew longer. Its energy fell lower. Its temperature, originally around 3,000 Kelvin, dropped steadily. Until today, it sits at approximately 2.7 Kelvin, on average, across most of deep space, barely above absolute zero. That ancient light is still with us. It fills the universe in every direction. It passes through you right now, through the walls of your room, through the entire Earth. Unimpeded, it carries no warmth you can feel, but its temperature can be measured precisely with the right instruments. It is called the cosmic microwave background, because at 2.7 Kelvin, its peak emission falls in the microwave part of the electromagnetic spectrum. 2.7 Kelvin, on average, the temperature of empty space, which turns out to be the temperature of the universe's oldest light, stretched by 13.8 billion years of expansion until its warmth is barely measurable. Every photon of this ancient light that passes through your room tonight has been traveling for almost the entire age of the universe. It carries within it, encoded in its wavelength and energy, the history of everything that has happened to space since the moment the fog cleared. That is what the temperature of empty space actually is. It is not the coldness of a refrigerator or a winter night. It is not the absence of a nearby fire. It is the residual warmth of the universe's beginning, spread across a volume of space so vast that the warmth has become nearly indistinguishable from silence. 2.7 Kelvin, on average, the temperature of nothing, which turns out to be the temperature of everything, seen from far enough away and long enough ago. Sit with that for a moment. Not the physics of it, just the image. You are lying in a room right now. The walls around you are at roughly room temperature. The air is similar, but passing through those walls, through you, through everything in this room and everything in this building, is a bath of ancient microwave light from the dawn of time, approximately 2.7 Kelvin on average, from every direction at once. It has been here longer than the Earth. It was here before the sun existed. It will be here long after both are gone. When you step outside on a clear night and look up at the stars, you are surrounded by this ancient light, not just from the visible stars, from the background itself, the microwave glow filling the entire sky in every direction. Invisible to your eyes, but real in every way physics can measure. You are inside a sphere of ancient light, 2.7 Kelvin, on average, in every direction. And the stars you can see are local exceptions to a universe that has otherwise cooled almost completely from its fiery beginning. The child asked why space is cold when the sun is hot. Now you know part of the full shape of the answer. The sun is hot because it is burning. Space is cold because it is old. And the 2.7 Kelvin background, filling the universe on average, is the universe remembering, in its own way, what it was before the stars arrived to warm it. Let your breathing slow a little more. Let the ancient light drift through you in the dark, as it always does, as it has been doing since before you were born, since before your parents were born, since before the earth existed. It carries no warmth you can feel, but it carries something more lasting than warmth. It carries the universe's memory of its own beginning. Stay where you are for a moment. Feel the stillness of the room, the weight of the pillow, the soft boundary between wakefulness and something quieter. And notice, if you can, the complete silence of everything passing through you right now. The ancient microwave light from the last chapter is still here, still crossing the room in every direction. You cannot feel it. You cannot hear it. But the instruments that have measured it have revealed it to be one of the most important things in the universe. And the story of how it was found is one of the most quietly extraordinary stories in the history of science. It begins not with a telescope pointed at the sky, but with a large horn-shaped antenna in a field in New Jersey, and two scientists who were trying very hard to get rid of a noise they could not explain. In the early 1960s, Bell Telephone Laboratories occupied a campus in Holmdel, New Jersey, with the unhurried atmosphere of a place where serious people were given time to think. Bell Labs was, at that moment, one of the most productive scientific institutions in the world. The transistor had been invented there. Information theory had been developed there. It was a place where the boundary between pure science and practical engineering was kept deliberately open. Among the instruments on the campus was a large horn-shaped antenna, originally built to communicate with early Telstar communications satellites. By the early 1960s, the satellite program had moved on, and the antenna was available for other purposes. Two young researchers named Arno Penzias and Robert Wilson began using it for radio astronomy. Almost immediately, they encountered a problem. Their measurements were contaminated by a persistent, low-level signal appearing uniformly across the sky. It was faint, but undeniable. A background noise that refused to go away, no matter how carefully they adjusted their equipment. The signal appeared equally strong in every direction they pointed the antenna, at all times of day, at all times of year. It showed no correlation with any known astronomical source. Penzias and Wilson were methodical in the way that good experimentalists are. They checked their receiver electronics. They accounted for every source of interference they could identify. They pointed the antenna at New York City to estimate the contribution of urban radio noise. They inspected the antenna itself, physically, discovered that pigeons had nested inside the horn, cleaned everything out thoroughly, and measured again. The signal was still there, at roughly the same time, entirely separately. A group of physicists at Princeton University, led by Robert Dick, were preparing to search for exactly this kind of signal. They had reasoned from theoretical principles that if the universe had begun in a hot, dense state and expanded and cooled over billions of years, the ancient radiation from that early phase should still be detectable today, cooled to a temperature of a few degrees above absolute zero, filling the sky uniformly in every direction. They were building their own detector to search for it when they received a telephone call from Penzias and Wilson. The two groups met. The theorists explained what they had predicted. The experimentalists explained what they had found. The match was immediate and unmistakable. Penzias and Wilson had spent months trying to eliminate a signal that turned out to be the oldest light in the universe. Both papers were published in the Astrophysical Journal in the year 1965. Penzias and Wilson described their observation. Dickey and his colleagues described the theoretical interpretation. Together, they announced that the echo of the Big Bang was real, detectable, and present in every direction at once. Penzias and Wilson received the Nobel Prize in Physics in the year 1978, but the discovery was only the beginning. The background radiation is almost perfectly uniform in every direction. But not quite. There are tiny temperature variations, fluctuations of approximately 1 part in 100,000, meaning some regions of the sky are infinitesimally warmer and some infinitesimally cooler than the average. These variations are so small that the first measurements could not detect them. Only with dedicated satellite missions did the full pattern become visible. The Kobe satellite, the Cosmic Background Explorer, launched by NASA in the year 1989, was the first instrument sensitive enough to map these variations. Its lead scientists, George Smoot of the Lawrence Berkeley National Laboratory and the University of California, Berkeley, and John Mather of NASA's Goddard Space Flight Center, announced the results in the year 1992. The variations were there, exactly as cosmological theory had predicted. Smoot and Mather received the Nobel Prize in Physics in the year 2006. The WMAP satellite, the Wilkinson Microwave Anisotropy Probe, launched in the year 2001, mapped the variations with significantly greater precision, and the Planck satellite, operated by the European Space Agency from the year 2009 to 2013, produced what remains the definitive map of the cosmic microwave background. What these maps show is a sky covered in a subtle pattern of warm and cool spots at every scale, like the surface of an orange peel seen from a great distance. The overall temperature is 2.725 Kelvin on average, precise to 3 decimal places. The variations around that average are measured in millionths of a degree. From those millionths of a degree, cosmologists have extracted an extraordinary amount of information. The age of the universe, 13.8 billion years. The composition of the universe, approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. The geometry of space itself, flat to within the precision of current measurements. All of this, from light that has been traveling for 13.8 billion years. All of this, from temperature variations of 1 part in 100,000. Take a moment with that. The oldest photograph ever taken, of the earliest moment that light was free to travel, hanging in the sky in every direction, and from the pattern of its almost imperceptible warmth, variations, we have learned the age and shape and composition of everything. Now bring this back to the question of why space is cold. The cosmic microwave background sets a temperature floor for most of the universe, even in the emptiest region of intergalactic space, far from any star or galaxy. A thermometer would read approximately 2.7 Kelvin on average, because this ancient radiation is there, filling all of space equally, pressing its faint warmth on every surface from every direction. It is the minimum across most of the cosmos. And it is not permanent. The universe continues to expand. The wavelengths of the background continue to stretch. Its temperature continues to fall. In another trillion years, the background temperature of the universe will be a fraction of what it is today, the ancient echo growing fainter still, drifting toward a cold the universe has never quite reached. But that is a very long time away. For now, approximately 2.7 Kelvin, on average, fills every corner of space in every direction. A faint and faithful record of what the universe was, still present in what the universe is. You are surrounded by it right now. Microwave photons from the early universe are passing through your walls, through your body, through everything around you. At this moment, and at every moment, they carry almost no energy. They warm nothing you could feel. But they have been traveling since before the sun existed, since before the earth, since before any star you can see in tonight's sky. Think of it this way. As you rest here, the cold of space is not an emptiness of energy. It is the presence of very old, very tired light, stretched by the expansion of the universe until its warmth is nearly gone, filling the cosmos as faithfully now as on the day it was released, 13.8 billion years ago. The echo is still ringing, faintly, everywhere, always. Let that settle as gently as you can. Let the ancient light pass through you in the dark and carry with it whatever quiet comfort there is in knowing that the universe carries its history in its temperature, and that the cold of space is not a void but a record of fire, grown very, very old. Picture someone standing outside at dusk, not in a city, somewhere quiet, where the horizon is wide and the sky is deepening, from gold to amber to the first thin blue of evening. They are watching the sun go down, that last warm light spreading flat across the land, still touching their face, even at this angle. Even this late in the day, they feel the warmth on their cheeks and the bridge of their nose and the backs of their hands. It is gentle now, softer than noon, but unmistakably there. And then, the sun dips below the horizon. Within minutes, the air begins to cool. The warmth fades from their face. Not because the sun has turned off. It is still there, burning just as brightly as it was a moment ago. 93 million miles away. But Earth has rotated that location out of direct line of sight. The radiation is no longer reaching them, and the warmth, which felt so present just moments before, begins to leave. They turn and walk back toward the house, through the door, into the warmth of a lit room. Hold that person there for a moment before we follow the physics. Because everything we are about to explore in this chapter is contained in that brief walk from the dusk back to the doorway. The warmth they felt was not in the air around them. It was in the radiation reaching them directly from the sun. The moment that line was interrupted, the warmth began to go, and the space between them and the sun, all 93 million miles of it, was neither warmer nor colder because of any of this. Now follow that radiation backward, all the way to its source. The sun obeys a law so fundamental that it governs every source of light and heat that radiates in all directions through three-dimensional space. It is called the inverse square law, and understanding it is the key to understanding why the sun's enormous output cannot warm the void between the stars. The sun radiates its energy outward equally in all directions. The energy spreads across the surface of an ever-expanding sphere as it travels. The surface area of a sphere grows with the square of its radius. Double the distance from the sun, and the same energy is now spread across 4 times the surface area. Triple the distance, and it is spread across 9 times the area. The energy per unit area, the intensity of the radiation reaching any given point, decreases with the square of the distance from the source. The Sun's total energy output is approximately 3.8 times 10 to the power of 26 watts, released continuously, in every direction, at the distance of Earth's orbit, 93 million miles from the Sun. That energy has spread across a sphere so enormous that Earth's cross-section intercepts only about 1/2 billionths of the total output. And yet that 1/2 billionths is enough to power everything on Earth's surface. The amount of solar energy arriving at the top of Earth's atmosphere per unit area, called the solar constant, is approximately 1,361 watts per square meter. This number drives weather, oceans, ecosystems, and civilization. 1,361 watts on every square meter of the sunlit side of Earth, arriving continuously from a fusion reactor 93 million miles away. Now follow the inverse square law outward and watch what happens to that number. At the distance of Mars, roughly 1.5 times Earth's distance from the Sun, the solar constant has dropped to approximately 589 watts per square meter, less than half of what Earth receives. Mars is cold, not only because it lacks a substantial atmosphere, but because it receives significantly less energy per square meter to begin with. At the distance of Jupiter, about 5 times Earth's distance from the Sun, the solar constant has fallen to approximately 50 watts per square meter. The enormous storms of Jupiter, the great red spot that has been spinning for centuries, the powerful winds in the banded atmosphere, are all driven by a solar input roughly 30 times weaker than what Earth receives. At the distance of Neptune, approximately 30 times Earth's distance from the Sun, the solar constant has fallen to approximately 1.5 watts per square meter. A single small nightlight produces more power than the Sun delivers to every square meter of Neptune's cloud tops. And beyond Neptune, in the vast region between our solar system and the nearest other star, the solar constant continues to fall. By the distance of 1 light year from the Sun, the intensity of solar radiation has dropped to a level that requires extremely sensitive instruments to detect. This is the first part of the answer to why the Sun's warmth does not spread outward and heat everything. The energy does spread outward. It spreads precisely as the inverse square law predicts, diluting with the square of distance, growing thinner until it becomes unmeasurable against the background. The Sun is not failing to radiate. Its radiation is simply becoming too dilute to warm anything significantly once it has spread across the enormous spheres corresponding to interplanetary and interstellar distances. But there is a second part to the answer, and it is the part that requires the understanding we have been building all night. The radiation that leaves the Sun does not warm the space it travels through. Not because the space is blocking it, because there is almost nothing in the space to absorb it. Recall what we established about how radiation becomes heat. A photon traveling through space carries energy, but it does not transfer that energy to its surroundings unless it is absorbed by something. A photon can travel for billions of years through empty space without warming a single cubic centimeter of vacuum, because the vacuum has almost no atoms to absorb it and convert its energy into molecular motion. The photon carries its energy faithfully, at the speed of light, until it finally encounters something willing to absorb it. Most of the radiation that leaves the Sun never encounters anything at all. It travels outward, spreading and diluting according to the inverse square law, until its intensity is negligible. Eventually, it becomes part of the general radiation background of the universe, its wavelength stretched by cosmic expansion, its energy distributed across the vast emptiness of intergalactic space. The radiation that does encounter something, a planet, a moon, an asteroid, a dust grain, that radiation is absorbed and converted to heat. The object warms. If the object has a way to lose heat through radiation of its own, It settles at the temperature where absorbed energy equals emitted energy. Earth is in exactly this equilibrium. It absorbs solar radiation and warms. It radiates its own infrared energy outward and cools. The balance between these two processes determines the average surface temperature. Now, return to the person who walked back into the house at dusk. Inside, the room is warm, not because the sun is currently heating it. The sun set minutes ago. The room is warm because the walls and floor absorbed solar radiation throughout the day, stored that energy as heat, and are now radiating it slowly back into the air. The sun heated the things. The things are now heating the room. And the space between the house and the horizon where the sun disappeared holds none of this warmth. It never did. This is the answer to the question. The sun does not heat space. It heats things, and space has almost none. The sun is generous. Space is vast, and the generosity of one cannot overcome the vastness of the other. Here is the thought I want to leave you with before we move on, because it connects the physics to something that feels personal, even though it is cosmic. The solar constant at Earth's orbit, 1,361 watts per square meter, is the precise result of the sun's output and Earth's distance. Change either by very much, and the number changes enough to matter enormously for conditions on the surface. Move Earth to the orbit of Mars, and the solar constant drops by more than half. Move it to the orbit of Venus, and it roughly doubles. The temperature of Earth, the temperature that allows liquid water and stable weather and the chemistry of life, is a function of being exactly this far from the sun. Not close enough to cook, not far enough to freeze. The cold of space is real. The inverse square law is impartial. And the warmth of this particular place, at this particular distance, is neither guaranteed nor permanent. It is, for now, exact, and exactness, in a universe this large, is worth noticing.
There is an object in most kitchens that contains one of the most elegant solutions to a physics problem ever placed in ordinary hands. Pick it up in your mind. Feel its weight. Light, probably, and smooth, and giving no indication of the engineering inside it. You have almost certainly owned one. You have used one without thinking about it, and unless someone pointed it out, you have probably never considered it as a device that defeats 3 separate mechanisms of heat transfer simultaneously, with no moving parts, no power source, and no ongoing maintenance required. It is a vacuum flask, the insulated bottle that keeps coffee hot for hours or keeps ice water cold through a summer afternoon. Invented in the 1890s by the Scottish chemist James Dewar, who needed a way to store extremely cold, liquefied gases in his laboratory. It became a household object so common that its underlying brilliance became invisible. But the brilliance is there, and understanding it, truly understanding it through what we have learned tonight, makes the object feel like something close to a small miracle of applied physics. The vacuum flask works by attacking all 3 pathways of heat transfer at once. The first pathway is conduction, heat conducted through direct contact, molecule to molecule, from the warm contents to the cooler surroundings, or vice versa. The flask addresses this by constructing a double-walled container with a vacuum between the walls. You will recall from our earlier chapters that conduction requires matter, a chain of molecules to pass vibration from one to the next. In a vacuum, that chain is broken. There are no molecules between the inner and outer walls to conduct heat in either direction. The vacuum is the insulator, and it is a nearly perfect one, because it contains almost nothing to carry vibration through. The second pathway is convection, heat carried by the movement of a fluid, air, or liquid, flowing from warm regions to cool ones. Convection also requires matter. In the vacuum between the walls of the flask, there is no air to circulate, no fluid to carry warmth from the inner wall to the outer. Convection is eliminated by the same vacuum that eliminates conduction. Two pathways defeated by one structural choice. The third pathway is radiation, and this is where the flask must work harder. Because radiation, as we have established, does not need matter. It crosses a vacuum as readily as it crosses air. The heat in your coffee will radiate infrared energy outward toward the cooler outer wall, regardless of the vacuum between them. To address this, the inner surfaces of a vacuum flask are silvered, coated with a reflective metallic layer. Reflective surfaces do not absorb radiation well. They return it. The infrared energy emitted by the warm coffee hits the inner wall, reflects back toward the coffee, and the energy stays where you want it. Similarly, any infrared radiation coming in from outside reflects off the surface of the inner wall and does not reach the contents. 3 pathways. 3 solutions. 1 object. The vacuum flask does not add heat or remove it. It simply places 3 carefully engineered barriers between the contents and the outside world, each one targeting a specific mechanism of thermal exchange. And the result is that the coffee stays hot for hours because it has almost nowhere for its heat to go. Now take that principle and apply it to a problem considerably larger and more complex than keeping coffee warm. Apply it to a human being in space. The suit worn by NASA astronauts during spacewalks is called the Extravehicular Mobility Unit. It is not a suit in any ordinary sense. It is a wearable spacecraft, a self-contained life support system, a pressure vessel, a thermal management system, and a micrometeorite shield, all in one garment that must be flexible enough to allow its wearer to move and work and sometimes spend 6 to 8 hours performing precise mechanical tasks in an environment that challenges survival in several simultaneous ways. The thermal challenge alone would be sufficient to make the suit extraordinary. Recall what we established about objects in space. Without an atmosphere to equalize temperature through conduction and convection, objects experience only radiative heat transfer. The side facing the sun receives intense solar radiation. The side in shadow radiates its own infrared energy into the cold void. The temperature difference between the two sides of any object can exceed 500 degrees Fahrenheit. The human body is not designed to manage this. The Extravehicular Mobility Unit addresses this through a construction that is, at its core, the Thermos flask problem solved for an irregularly shaped, heat-generating, mobile object that needs to breathe. The outer layer of the suit is made of a material called orthofabric, a blend that reflects a significant portion of incoming solar radiation rather than absorbing it. Beneath that are multiple layers of aluminized mylar film, thin sheets of plastic coated with aluminum, which function like the silvered walls of the thermos, returning infrared radiation rather than absorbing it. There are more than a dozen of these layers, each separated from the next by a spacer material, and the whole assembly addresses both radiation management and protection against tiny high-speed particles simultaneously. But the spacesuit faces a problem the Thermos flask does not. The Thermos contains coffee, which passively gains or loses heat and simply needs to be slowed down. The astronaut inside the suit is constantly generating heat through metabolism, through the work of moving and breathing and maintaining a body temperature of 98.6 degrees Fahrenheit. That heat must go somewhere, or the astronaut overheats, regardless of how well insulated the suit is. In a normal environment, the body loses excess heat through convection, through evaporation of sweat, through radiation. In a sealed, pressurized suit, convection is eliminated, and sweat evaporation is complicated and limited. The solution is active thermal control, and it is the feature that most directly shows the ingenuity of going beyond the thermos, woven into a garment called the liquid cooling and ventilation garment. Worn next to the astronaut's skin is a network of thin plastic tubes totaling roughly 90 meters in length. Through these tubes, water is continuously circulated at a controlled temperature. The water absorbs excess body heat directly from the skin, carries it to a device called the sublimator in the backpack life support system. And there the warm water transfers its heat to a separate water circuit that releases it to space through the controlled evaporation of ice. The ice is consumed over the course of the spacewalk. The astronaut stays cool. 90 meters of tubing, circulating water against skin, releasing heat through ice, keeping one human body alive in 500 degrees of difference. This system is the body's own sweating mechanism, reimagined for an environment where sweat cannot evaporate into surrounding air. It handles the thermal output of a working human body in the most thermally challenging environment accessible from Earth. And it does so reliably enough that astronauts have performed spacewalks lasting more than 8 hours. What the spacesuit represents, seen through the lens of everything we have learned tonight, is the complete application of our understanding of heat transfer to the protection of a single human life. The multi-layer insulation stack manages radiation. The pressurized interior eliminates conduction from the vacuum outside. The active water cooling system manages the heat the body itself produces, routing it through a controlled pathway to a controlled exit. The Thermos, Flask, and the Spacesuit are separated by a century of technology and an enormous difference in complexity. But they are the same idea. Know how heat moves. Block every pathway you want to block. Manage the ones you cannot block. Control the outcome. There is something worth sitting with here, at the intersection of the cosmic and the practical. The question of why space is cold, the question that started our night together, is not merely an intellectual puzzle about astronomical environments. It is a question whose answer is embedded in every vacuum flask ever made, every spacesuit ever worn, every building insulation system, every thermal management system in every satellite and spacecraft that humans have ever built or will build. Understanding heat is not separate from the practical world. It is woven through every attempt we have ever made to maintain warmth in a cold environment or coolness in a hot one. Which is to say, it is woven through almost everything we have ever built. The same physics that explains why space is cold is the physics that keeps your coffee warm and your orange juice cold, and that kept the Apollo astronauts alive on the surface of the moon. The equations do not care whether they are being applied to the cosmos or to a kitchen shelf. They work the same way in both places, because the universe has only one set of rules, and it applies them everywhere equally. That consistency, that single set of rules, operating from the quantum scale, to the cosmic scale, from a thermos flask to the temperature of the universe itself, is one of the things that makes physics, at its best, feel not like a collection of facts, but like a single coherent story. We have been reading that story tonight, and the next chapter adds to it something that should, by all ordinary logic, not be possible. Something that the sun does that appears to defy our everyday intuition about how heat should behave. Something that physicists noticed more than a century ago, puzzled over for decades, and are still, today, working to fully explain. It is one of the most persistent open mysteries in the science of our own star, and it is waiting just ahead. Rest here for a moment before we go to meet it. The coffee is still warm in the flask. The astronaut is still breathing, cooled by 90 meters of circulating water, surrounded by 500 degrees of difference on either side. The same physics, the same three mechanisms, holding everything in its place. And outside, 93 million miles away, the sun still burning through another moment of hydrogen, sending its radiation outward in all directions, warming whatever is willing to absorb it, and leaving the space between almost untouched, as it always has, as it will, for approximately 5 billion years more. Close your eyes for just a moment and picture fire. Not a specific fire, just the idea of it, the orange and yellow movement, the warmth pressing outward, the intuitive sense that fire and heat belong together, that wherever there is flame, there is high temperature, and wherever there is high temperature, there is, in some sense, fire. Stay with that picture. Let it be as complete and as certain as it has always felt, and then let tonight gently take it apart. Temperature, it turns out, is not a property of the universe that clusters in the range of human experience, the range of temperatures that actually exist, from the coldest achievable in a laboratory to the hottest conditions physics can describe, is so vast that the entire range a human being encounters in daily life, from the cold of a winter morning to the heat of an oven, occupies a fraction so small it barely registers on the full scale. We are creatures of a very narrow band, and almost everything interesting about temperature in the universe happens outside that band. Let us walk the full scale together, slowly, from cold to hot, and let each step quietly reframe what you think you know. Start where we have been, approximately 2.7 Kelvin, on average across the deep spaces between galaxies, the temperature of the cosmic microwave background, the ancient light filling the universe from every direction, colder than any winter, colder than any natural place on Earth, barely above the absolute floor. Move upward. Nitrogen becomes a liquid at 77 Kelvin, approximately negative 321 degrees Fahrenheit. Liquid nitrogen is cold enough to freeze flowers instantly, to shatter rubber, to produce dramatic clouds of condensation in warm air. It is used in medicine, in food preparation, in laboratories to cool sensitive instruments. And yet, at 77 Kelvin, it is nearly 30 times warmer than the average background temperature of space. Water freezes at 273 Kelvin, 0 degrees Celsius. A fact so embedded in daily life that it is easy to forget it represents an arbitrary point on a scale extending more than 200 degrees below it and billions of degrees above. The surface of the human body, approximately 310 Kelvin. A comfortable room temperature, around 300 Kelvin. A hot oven, perhaps 500 to 550 Kelvin. The temperature at which wood ignites, approximately 560 Kelvin. The surface of a candle flame, roughly 1000 to 1500 Kelvin, depending on which part of the flame you measure. Now the scale begins to open up. The surface of the Sun, approximately 5778 Kelvin, more than 10 times hotter than a candle flame, hot enough that atoms in the outer layers are moving so fast they strip electrons from each other through collisions, creating a plasma, a state of matter in which electrons roam freely rather than being bound to individual atoms. The visible light that warms your face on a summer afternoon comes from this surface, and it has the orange-white color it does, because that temperature corresponds to peak emission in the visible part of the electromagnetic spectrum. A lightning bolt reaches approximately 30,000 Kelvin in its core, roughly 5 times hotter than the surface of the Sun. In the fraction of a second it exists. This is why lightning produces brilliant white light. Its temperature pushes peak emission into the ultraviolet, and the visible light it produces spans the full spectrum nearly equally. The core of the Sun, where nuclear fusion actually occurs, reaches approximately 15 million Kelvin, not the surface you see, the hidden interior, beneath hundreds of thousands of kilometers of plasma, where hydrogen nuclei are fused into helium, releasing the energy that powers everything. A supernova, the explosion of a massive star at the end of its life, generates temperatures in its core of billions of Kelvin in the moments of collapse. The resulting neutron star has a surface temperature immediately after formation of approximately 1 million Kelvin, and a core temperature that may reach into the trillions of Kelvin in the first moments of its existence. This is the scale, from approximately 2.7 Kelvin on average, to temperatures in the early universe that exceed any number with a comfortable name. And somewhere near the lower middle of that enormous range, in a band from roughly 300 to 1000 Kelvin, sits everything that human beings have ever called hot or cold in ordinary conversation. Now, within this scale, something interesting happens when you look at stars specifically. Not all stars are the same temperature, and the range of stellar surface temperatures is both broader and stranger than most people expect. The hottest stars, the massive blue-white giants called O-type stars, have surface temperatures of 30,000 to 50,000 Kelvin. They burn so hot that they emit most of their energy in the ultraviolet, invisible to human eyes. They are brilliant, but they burn through their fuel so rapidly that they live for only a few million years, which, on cosmic timescales, is barely a moment. The Sun, by contrast, is a middling yellow star with a surface temperature of about 5,778 Kelvin and an expected total lifespan of roughly 10 billion years, of which about 4.6 billion have already passed. The coolest true stars are the red dwarf stars, the most common type in the galaxy. Their surface temperatures range from about 2,400 to about 3,900 Kelvin. They are so dim that not a single red dwarf is visible to the naked eye from Earth. Despite the fact that red dwarfs make up approximately 70% of all stars in the Milky Way, they burn so slowly that some have estimated lifespans measured in trillions of years, far longer than the current age of the universe. But stars have a lower boundary. a minimum temperature below which they are not true stars at all. Nuclear fusion in a stellar core requires a minimum mass and a minimum core temperature to sustain itself. Objects larger than planets, but not quite massive enough to ignite sustained hydrogen fusion, are called brown dwarfs. And they represent an interesting twilight zone between stars and planets. They generate some heat from slow gravitational contraction and from limited fusion processes, but not enough to sustain them as true stars. They glow faintly and cool slowly over billions of years. The coolest known brown dwarfs push the definition of astronomical temperature into genuinely surprising territory. An object designated WISE 0855-0714, discovered using data from NASA's Wide Field Infrared Survey Explorer satellite and announced in the year 2014 by astronomer Kevin Luhman of Pennsylvania State University, has an estimated surface temperature of approximately 225 to 260 Kelvin, placing it among the coldest known brown dwarfs. That is roughly -40 to -10 degrees Fahrenheit, the temperature of a cold winter day in the northern states, or a night on the Arctic tundra. There is an object in space, more massive than Jupiter, but not quite a star, with a surface approximately as cold as the harshest winter air you have ever felt on your face. This object is colder than a household oven, colder than the temperature required to bake bread, and yet it drifts through space as an astronomical object, formed from a collapsing gas cloud, classed among the stellar family in the broadest sense, with a surface temperature that a person might describe as merely unpleasant rather than immediately lethal from heat. The universe does not divide neatly into hot things and cold things based on any categories we find convenient. Now to the fire that is colder than stars. The coolest flames that can be produced under controlled conditions are called cool flames, and they were not widely studied until relatively recently because they are difficult to sustain in normal gravity. Cool flames occur when certain fuels burn in low oxygen environments at temperatures between approximately 500 and 900 Kelvin, low enough that the combustion process proceeds slowly through chemical chain reactions that do not produce the typical orange glow of an ordinary flame. They are nearly invisible to the naked eye. They produce little light and moderate heat. NASA researchers have studied cool flames extensively aboard the International Space Station, where microgravity allows combustion experiments impossible on Earth. Beginning in the year 2012, astronauts performed experiments called the Cool Flames Investigation, burning droplets of fuel in microgravity and discovering that flames can sustain themselves at temperatures significantly lower than previously thought possible, with key results continuing to emerge in subsequent years. These experiments have implications for engine efficiency and combustion design that are relevant to engineering right here on Earth. Cool flames burn at temperatures between roughly 500 and 900 Kelvin. The surface of a red dwarf star burns at 2,400 to 3,900 Kelvin. The flame in your kitchen is cooler than the coolest true star, the brown dwarf we mentioned, with its surface at roughly 225 to 260 Kelvin, is cooler than any flame, an astronomical object formed like a star, cooler than a match. Let that sit for a moment. A star cooler than a candle, a flame cooler than a star. The universe does not respect the intuitive categories that daily life encourages: hot and cold, fire and ice, star and void. These are human distinctions that the universe accommodates approximately in the middle of its temperature range and ignores entirely at the extremes. What the full temperature scale reveals, when you step back and look at it whole, is something about the position of human experience within the universe. We exist in a narrow band. The temperatures we can survive without technological assistance range from perhaps 240 Kelvin to about 320 Kelvin. Our technology extends our range somewhat. But even with technology, we operate in a sliver of the total scale, so thin it is barely visible when plotted against the full range from absolute zero to the temperatures of the early universe. Everything we call hot is cold to a neutron star. Everything we call cold is blazing to a region of deep intergalactic space. The campfire that warmed early humans for hundreds of thousands of years burns at temperatures 1,000th of the sun's surface. The sun's surface is a fraction of a supernova core. We are, thermally speaking, creatures of the middle, neither the fire nor the void, neither the beginning nor the end, comfortable, briefly, in the narrow warmth between extremes that we did not create and cannot ultimately change. And yet within our narrow band, we have learned to read the full scale. We have built instruments sensitive to 2.7 Kelvin and instruments capable of measuring temperatures in the billions of Kelvin. We have extended our thermal senses far beyond the narrow range our bodies can survive in. And in doing so, we have mapped a universe far stranger and far more varied than anything our ordinary experience of hot and cold would suggest. There is one more temperature anomaly worth sitting with before we move on. One that lives not in the distant cosmos, but in the star that warms you every day. One that physicists noticed more than a century ago and have been working to explain ever since. It involves the outer atmosphere of the sun, and it appears, in a way that is still not fully resolved, to defy our everyday intuition about how temperature should behave as you move away from a heat source. It is one of the oldest open questions in solar physics, and it is waiting in the next chapter. There is a rule so fundamental to our experience of heat that we absorb it before we have words to describe it. Move away from a fire and you get cooler. Stand close to a radiator and you feel warm. Step back and the warmth fades. Sit beside a campfire and the heat presses against your face. Walk away into the dark and the cold returns. This is not a law we learn in school and then apply to the world. It is something our bodies know before our minds do, encoded in every interaction we have ever had with warmth. It is as basic as the fact that things fall when you drop them. The outer atmosphere of the sun appears to violate our everyday intuition about this completely. Not subtly, not in a way that requires sensitive instruments to detect. The apparent violation is enormous, a factor of hundreds, and it has been known to science for more than a century without being fully explained. It is one of the most persistent open problems in solar physics, and its persistence speaks honestly to how much the universe is still willing to withhold, even from careful and dedicated inquiry. Our nearest star, the most studied astronomical object in history, is still keeping a secret. Here is what we know. The visible surface of the sun, the layer that produces the light you see on a clear day, is called the photosphere. Its temperature is approximately 5,778 Kelvin. Hot by any human standard, but a precise and measurable value that fits neatly within the physics of thermal emission. Above the photosphere is a thin layer called the chromosphere, the Sun's lower atmosphere, extending a few thousand kilometers above the surface. Its temperature rises as you move upward through it, from about 4,000 Kelvin at its base to roughly 20,000 Kelvin at its upper boundary. Already, this is unexpected. Moving upward, away from the heat source, and the temperature is rising rather than falling. Above the chromosphere lies the corona. The corona is the Sun's outer atmosphere, extending millions of kilometers into space and visible during a total solar eclipse as the pearly white halo surrounding the darkened disk of the Moon. And its temperature, measured directly by instruments and confirmed by the specific wavelengths of light it emits, is between 1 million and 3 million Kelvin. Not 5,000, not 50,000, 1 million to 3 million Kelvin. The surface of the Sun is approximately 5,778 Kelvin. The atmosphere above the surface is 1 million to 3 million Kelvin. You move away from the fire, through a region of intermediate temperature, and then the temperature increases by a factor of roughly 500. Pause here for a moment, just to feel the strangeness of that. A factor of 500, not a measurement artifact, not an instrument calibration issue. This has been confirmed by decades of observation from ground-based telescopes, from space-based instruments, including the Solar and Heliospheric Observatory, launched in 1995, the TRACE satellite, the Hinode spacecraft, and the Solar Dynamics Observatory, launched in the year 2010, and most recently by the Parker Solar Probe, launched in 2018, which has made closer passes to the Sun than any previous spacecraft in history. The coronal heating problem asks a simple question. Where is the energy coming from? The corona is losing energy continuously. It radiates light across a broad spectrum. It accelerates particles outward as the solar wind to maintain its temperature of 1 to 3 million Kelvin. It must be receiving energy from somewhere at a rate sufficient to replace everything it loses. The surface below it is 500 times cooler. Energy does not spontaneously flow from a cooler region to a hotter one. That would violate the second law of thermodynamics. So the energy must be coming from somewhere else, carried by some mechanism that does not depend simply on the temperature difference between the surface and the corona. Two main categories of explanation have been proposed and studied seriously over the decades. The first is wave heating. The Sun's surface is not calm. It is a churning, boiling plasma, with convective cells, called granules, rising and falling continuously, each one roughly the size of a large American state, lasting approximately 10 minutes before cooling and sinking back. This turbulent surface generates waves, oscillations in the magnetic field and in the plasma itself, that propagate upward into the corona. The proposal is that these waves carry energy from the convective surface layer upward into the corona, where they dissipate and deposit their energy as heat. The specific waves most discussed are called Alfvén waves, oscillations in magnetized plasma, first described theoretically by the Swedish physicist Hannes Alfvén, who received the Nobel Prize in Physics in the year 1970 for his work on magnetohydrodynamics. Let that name and that idea rest there for a moment. Waves in magnetized plasma, propagating upward from the surface of the Sun into its million-degree corona, carrying energy the way water waves carry energy across an ocean surface. It is a beautiful mechanism, even if it is still being measured and debated. The detection of Alphen waves in the corona has been confirmed by observations from several missions. Whether they carry enough energy to account for the full magnitude of coronal heating remains an area of active research. The second main category is nanoflare heating, a concept proposed by the solar physicist Eugene Parker in a paper published in the year 1988. Parker, who also predicted the existence of the solar wind before direct measurements confirmed it, suggested that the corona might be heated not by large-scale wave dissipation, but by an enormous number of tiny explosive events, each one individually too small to detect, but occurring so frequently across the entire solar corona that their collective energy output is sufficient to maintain the coronal temperature. These tiny events, which Parker called nanoflares, would result from the continuous braiding and reconnection of magnetic field lines in the corona. The Sun's magnetic field is complex, generated by the churning motion of charged plasma in its interior, and the field lines threading through the corona are continuously twisted and tangled by the motion below. When magnetic field lines of opposite orientation are forced together and reconnect, in a process called magnetic reconnection, energy stored in the magnetic field is released suddenly, heating the local plasma. If this happens millions of times per second across the entire corona, the cumulative effect could explain the heating. The Parker Solar Probe, named in honor of Eugene Parker, who lived to see its launch and initial results before his death in the year 2022, is designed partly to measure the corona and solar wind at unprecedented proximity. Its data has provided new constraints on both wave heating and nanoflare models. The current understanding in the field is that both mechanisms are probably operating simultaneously, with their relative contributions varying across different regions of the corona and different levels of solar activity, but a definitive quantitative accounting that fully explains coronal heating from first principles has not yet been achieved. This is worth stating plainly. Without apology, we do not yet fully understand why the outer atmosphere of our own star appears to be 500 times hotter than its surface. We have been studying the Sun with dedicated scientific instruments for more than a century. We have sent spacecraft to within a few million kilometers of its surface. We have measured its magnetic field, its acoustic oscillations, its neutrino output, its coronal emission at every wavelength, from radio to X-rays. We know its mass to 5 significant figures, its age to within a few 100 million years, its internal structure through a discipline called helioseismology that uses the Sun's natural oscillations the way a doctor uses ultrasound. We can predict solar eclipses centuries in advance. And we do not yet fully know why the atmosphere above its surface appears to be 500 times hotter than the surface itself. There is something important in this that goes beyond the specific problem. It is a reminder that proximity does not guarantee understanding. The Sun is not a distant object at the edge of our observational capability. It is our nearest star, the source of essentially all the energy that makes life on Earth possible, and it is still showing us things we cannot fully explain. The Parker Solar Probe has already made discoveries that were not anticipated. It found that the solar wind closer to the Sun is structured differently than models predicted, with sharp reversals in the magnetic field direction called switchbacks that appear and disappear over timescales of minutes to hours. Each measurement is a new constraint on the models. And the models are changing as a result. The coronal heating mystery will be solved. Not tonight, probably not this year, but within the careers of scientists currently working on it. If history is any guide, when the solution comes, it will teach us something more general about how energy moves in magnetized plasmas. Knowledge, with applications ranging from fusion energy research on Earth to our understanding of stellar atmospheres throughout the galaxy. For now, the mystery stands. Our star, 93 million miles away, burning quietly, keeping its last secrets behind a wall of million-degree plasma that the best instruments we have ever built are only now beginning to read. There is something almost companionable about this. If you let it be, the universe is not a solved problem. It is an ongoing conversation. And the sun, your sun, the one that warmed your face this afternoon and will rise again tomorrow morning, is still teaching us things we did not know. It has been patient this long. Remove everything, not dramatically, just in your mind, quietly. Begin stripping away, layer by layer, the things that make this planet what it is. Remove the oceans first. The vast bodies of liquid water covering more than 70% of the surface, storing heat and releasing it slowly, moderating temperature swings between day and night. Remove the forests and grasslands, the ice sheets, the soil and rock. Strip away everything until you have only a bare rocky sphere at this distance from the sun. And then do one more thing. Remove the atmosphere, not thinned, removed entirely. Every molecule of nitrogen, oxygen, carbon dioxide, water vapor, methane, and the trace gases that make up the thin shell of air wrapped around the planet. Gone. Now ask the question, what temperature would the surface reach? The calculation is not complicated. Take the solar constant, approximately 1,361 watts per square meter, arriving at the top of the atmosphere. Account for the fact that Earth is a sphere, distributing that energy across the whole surface rather than just the sunlit face. Account for the approximately 30% of incoming light that reflects away from clouds and bright surfaces without being absorbed. Calculate the temperature at which the surface would need to radiate infrared energy to balance the incoming solar energy. The answer is approximately -18 degrees Celsius, 0 degrees Fahrenheit. The temperature at which water freezes, the actual average surface temperature of Earth, is approximately +15 degrees Celsius, 59 degrees Fahrenheit. The difference between those two numbers, 33 degrees Celsius, is the greenhouse effect, the warming provided by the atmosphere above and beyond what the sun alone would produce at this distance, 33 degrees. That is the margin between the planet we have and a planet where liquid water barely exists at the surface, where the oceans we know would be frozen solid, where the weather systems and biological processes that characterize Earth would not be possible. The greenhouse effect is not a recent discovery, and it is not primarily the result of human activity. It is a fundamental feature of any planet with an atmosphere containing gases that absorb infrared radiation, and understanding it requires one more detail about radiation, a detail we have been building toward throughout the earlier chapters. The sun emits radiation primarily in the visible and near-infrared parts of the spectrum, because its surface temperature of about 5,778 Kelvin corresponds to peak emission at visible wavelengths. This radiation passes through Earth's atmosphere relatively freely, Most of the greenhouse gases are largely transparent to visible light. The sunlight reaches the surface. The surface absorbs the visible light and warms. A warmed surface emits radiation of its own, but at a much lower temperature, roughly 250 to 300 Kelvin rather than nearly 6,000 Kelvin. Lower temperature emission corresponds to longer wavelengths. The surface emits primarily in the thermal infrared, wavelengths much longer than visible light, invisible to the eye but detectable as heat. And here is where the atmosphere intervenes. The greenhouse gases, primarily water vapor, carbon dioxide, methane, nitrous oxide, and ozone, are largely transparent to incoming visible light but absorb outgoing infrared radiation. They intercept the infrared energy trying to escape from the surface, absorb it, and re-emit it in all directions, including back toward the surface. The surface receives some of this re-emitted energy and warms further. A more precise way to think about this is that the atmosphere acts as a selective absorber and re-emitter, open to certain wavelengths of incoming energy and partially opaque to the outgoing wavelengths trying to leave. It creates the 33-degree warming by admitting sunlight freely and slowing the escape of infrared. And the amount of warming depends on how much absorbing gas is present. Different greenhouse gases absorb infrared radiation at different wavelengths. Water vapor is the most abundant and responsible for the largest fraction of the natural greenhouse effect. Carbon dioxide absorbs strongly at wavelengths where water vapor does not, filling in gaps in the absorption spectrum and contributing meaningfully to the total warming. Methane is a much more potent absorber per molecule than carbon dioxide, but is present in much smaller quantities. Each gas has its own fingerprint in the infrared spectrum, determined by the specific vibrational and rotational modes of its molecular structure. Now look at what happens when you vary the greenhouse effect, using the solar system's other rocky planets as experiments that nature has already run. Venus sits at a distance from the Sun, about 72% of Earth's distance. Based on distance alone, it should be somewhat warmer than Earth. Venus also reflects away about 77% of incoming sunlight due to its dense cloud cover, a reflectivity so high that its base temperature before the greenhouse effect would be approximately negative 46 degrees Celsius. The actual surface temperature of Venus is approximately 465 degrees Celsius, 730 degrees Fahrenheit, hot enough to melt lead, the hottest surface of any planet in the solar system, including Mercury, which is closer to the Sun. Stop there for just a moment. Feel that number, 465 degrees Celsius. On a planet that without its atmosphere would be colder than Earth, every degree of that difference, more than 500 degrees of warming, is the Venusian greenhouse effect. Venus has an atmosphere composed of approximately 96% carbon dioxide, with a surface pressure roughly 90 times Earth's. The selective absorber became so thick, so opaque to outgoing infrared, that the surface temperature climbed to conditions hostile to any chemistry we associate with life. Mars presents the opposite example. Mars has an atmosphere composed primarily of carbon dioxide, similar in composition to Venus, but at a surface pressure less than 1% of Earth's. The total amount of greenhouse gas is simply too small to provide significant warming. The average surface temperature of Mars is approximately negative 60 degrees Celsius. and it varies enormously between day and night. From about 30 degrees Celsius on a summer afternoon near the equator to negative 140 degrees Celsius on a winter night near the poles. Mars is cold, not primarily because it is farther from the Sun, though that reduces the solar constant to about 43% of Earth's value. It is cold primarily because its atmosphere is too thin to retain the heat that does arrive. The energy that warms the surface during the day radiates back to space during the night with almost nothing to hold it in. Earth sits between these extremes. Its atmosphere is thick enough and contains enough greenhouse gases to provide 33 degrees of warming, not so thick that the greenhouse effect runs away, as it did on Venus, not so thin that the surface freezes solid every night as it does on Mars. The climate system of Earth is not static. It has never been static. The concentration of carbon dioxide in the atmosphere has varied enormously over geological time, from levels several times the current concentration during warm periods of Earth's history to levels significantly lower during ice ages. Each change in atmospheric composition produced corresponding changes in surface temperature, with the relationship between the two tracking the physics of the selective absorber with the consistency you would expect from a physical law applied to a planetary atmosphere. The physics does not care about the source of the change. Additional greenhouse gases produce additional warming, regardless of whether they originate from volcanic eruptions, from the burning of ancient organic carbon, or from any other process. The atmosphere responds to concentrations and absorption properties of the gases present. Temperature follows. This relationship has been confirmed by laboratory measurements of the infrared absorption properties of greenhouse gases, by the geological record of past climates and their correlation with past atmospheric compositions, and by the direct measurement of energy flows in and out of Earth's atmosphere by satellites. The greenhouse effect began as a gift, 33 degrees of warming that turned a frozen rock into a habitable world. The same physics that made that gift possible also describes what happens when the concentrations of absorbing gases change. Venus shows one endpoint of that process, Mars shows another, and Earth occupies the middle of a range that its particular history of geology and biology and more recently industrial activity has produced. The warmth you feel tonight, the comfortable temperature of the air around you, is the greenhouse effect working as it has worked for billions of years. Energy from the sun arriving as visible light, being absorbed by the surface, being remitted as infrared, and being partially retained by the atmosphere before escaping to space. A cycle as old as the atmosphere itself, as fundamental to the conditions of your existence as the distance from the sun or the presence of liquid water. The physics of heat that we have been following all night through the void of space arrives here at your own planet and becomes not abstract but immediate. The warmth that allows you to lie comfortably right now is the greenhouse effect in action. A layer of air above you, a few dozen kilometers thick, selectively absorbing and re-emitting infrared energy according to laws that apply equally on Earth, on Venus, on Mars, and on every planet orbiting every star in the observable universe. The same rules everywhere, producing very different outcomes depending on the inputs. And here, for reasons of chemistry and distance and history, producing the outcome in which you exist and can ask about them. Imagine standing at the edge of a city at night. Behind you, the lights, the warmth of buildings, the glow that softens the darkness in every direction and presses back the cold with the mere fact of its presence. Walk away from the city into open countryside, and you can still see the light on the horizon. Still feel the faint comfort of knowing it is there. Walk further, the glow fades. The stars become sharper. The darkness becomes more complete. And at some point, far enough out, you reach a place where the city might as well not exist, where its light no longer reaches you, where the warmth it represented has become an abstraction. The edge of the solar system is like that. And beyond it, the cold that waits has a character unlike anything in human experience. There is a boundary that no human being has ever crossed. It has no fence, no marker, no color, no texture, no sound. You cannot see it from Earth or even from orbit, but it is real, precisely located, and continuously monitored by instruments aboard the only human-made objects that have ever passed through it. It is called the heliopause, and it marks the edge of the sun's direct reach. Out beyond the planets, beyond the scattered debris of comets and ice in the distant reaches of the solar system, the sun produces a continuous outflow of charged particles called the solar wind. This wind streams outward in all directions, at speeds of roughly 400 to 800 kilometers per second, filling the space around the sun with a bubble of solar material that extends far beyond the orbit of Neptune. The boundary of this bubble, where the pressure of the solar wind finally becomes too weak to push back against the incoming pressure of interstellar material, is the heliopause. Voyager 1, the spacecraft we have met earlier tonight, crossed this boundary with confirmation coming in the year 2013, published in the journal Science by a team led by physicist Don Gurnett of the University of Iowa. Analysis of plasma wave data indicated that the spacecraft had likely entered interstellar space in August of the year 2012, with the formal confirmation established through the 2013 publication. For the first time in the history of our species, a human-made object had left the sun's immediate environment and entered interstellar space. What Voyager 1 found on the other side was a measurably different environment. Different populations of charged particles, a different magnetic field orientation, different radiation levels. In terms of temperature, what it found requires careful unpacking, because temperature in interstellar space is one of the most counterintuitive concepts in all of astrophysics. The space between stars is not uniform. It is not simply the cold vacuum we might picture when we imagine empty space. It is a complex and varied environment, structured by the physics of stellar radiation, magnetic fields, gravity, and the history of stellar explosions reaching back billions of years. Astronomers call this environment the interstellar medium, and it has regions of very different character. The coldest and densest regions are called molecular clouds. These are vast concentrations of gas and dust where hydrogen exists primarily in molecular form. The temperatures in the densest cores of molecular clouds are approximately 10 Kelvin, a few degrees above the average temperature of the cosmic microwave background. These regions are so cold and dense that the interstellar radiation field cannot penetrate them. They are also the birthplaces of stars. Gravity slowly pulls the dense gas inward, and if conditions are right, a core collapses and ignites, creating the next generation of stellar light. The warm neutral medium, a phase of interstellar gas where hydrogen exists as neutral atoms, occupies much of the volume of the galaxy at temperatures between approximately 6,000 and 10,000 Kelvin. Do not let the word warm mislead you. The density of matter in this phase is roughly 1/10 of an atom per cubic centimeter, compared to the 27 billion atoms per cubic centimeter in the air you are breathing. At that density, the high temperature reflects the speed of individual atoms rather than any significant thermal energy per unit volume. You could not warm your hands in this medium. There is simply not enough matter hitting them per second to transfer meaningful heat. The hot ionized medium is perhaps the most startling phase in terms of its temperature. This is gas that has been heated to temperatures of roughly 1 million Kelvin or higher by the shock waves from supernova explosions. Its temperature makes it technically the hottest common phase of interstellar matter, but its density is so low that it contains almost no thermal energy in practical terms and would produce no sensation of warmth on any surface exposed to it. This brings us back to the distinction we have visited several times tonight. Temperature and thermal energy are not the same thing. A region can have a very high temperature, meaning very fast-moving particles, while containing so little matter that the total energy available to heat any surface is negligible. Beyond our galaxy, in the vast spaces between galaxies, the environment becomes even more extreme in its emptiness. The intergalactic medium contains perhaps 1 hydrogen atom per cubic meter on average in some regions. The radiation temperature of this space, the quantity most relevant to the thermal environment of any object floating far from any heat source, approaches the cosmic microwave background temperature of approximately 2.7 Kelvin on average across most of this emptiness. 2.7 Kelvin on average. The floor across most of deep space. Now follow what this means for Voyager 1. Currently, somewhere beyond the heliopause, traveling through the local interstellar medium at approximately 61,000 kilometers per hour. The spacecraft is no longer inside the bubble of solar material. The Sun now contributes negligibly to the local radiation environment. Voyager 1 still carries a small nuclear power source, a radioisotope thermoelectric generator, which produces heat from the natural radioactive decay of plutonium-238. This is the only reason Voyager 1 has any instruments still operating. Though the power output has been decreasing steadily since launch, and several instruments have already been shut down to conserve energy for the remaining ones. Without that power source, Voyager 1 would gradually cool toward the temperature of its radiation environment. In interstellar space, this would eventually approach something between the interstellar radiation field and the cosmic microwave background, within a few Kelvin of 2.7 on average, cold in a way that has no analogue in any human experience. The Sun's warmth does not project into interstellar space in any meaningful way. The solar system is, in a thermal sense, a small, bright island in a sea of cold. The island is bounded by the heliopause. Beyond that boundary, the temperature of the radiation environment drops toward the cosmic microwave background average, and the Sun becomes simply one more dim point of light in a sky full of them. The nearest other star, Proxima Centauri, at 4.24 light-years away, maintains its own small, warm island in the same cold sea. Between those islands, in approximately 4 light-years of interstellar space, there is no meaningful warmth from either star. The temperature of that space is set by the cosmic microwave background on average, and the local contributions of whatever interstellar gas phases happen to occupy it. The galaxy is mostly cold. The stars are exceptions. Brief, brilliant, local exceptions, each warming a small bubble of space around itself. All of them together, maintaining the radiation temperature of the galaxy at values somewhat above the cosmic microwave background, near enough to enough stars to matter. But the cold between them is the default. The stars are the rare events. The cold is what space is when left to itself. Think about what the spacecraft our civilization built is doing right now. Launched by human hands in California in the year 1977, powered by the decay of plutonium, carrying a golden record of human voices and music and the sounds of a living planet, moving through interstellar space at 61,000 kilometers per hour, still sending its faint signal home across a distance that grows with every passing hour, crossing a region where the dominant temperature is set not by any star, but by the ancient light of the Big Bang. We sent something into the deep cold, and it is still going. That matters in ways that are difficult to fully put into words, but that feel true when you sit with them quietly in the dark. Every measurement has a limit below which it becomes meaningless. You can measure the length of a room to the nearest meter, to the nearest centimeter, to the nearest millimeter, but at some point, the measurement encounters a boundary imposed not by the precision of your instruments, but by the nature of what you are measuring itself. A boundary built into reality. Temperature has a limit of exactly this kind. We established early in tonight's journey that temperature measures the average thermal motion of molecules. As temperature decreases, that thermal motion slows. At some point, it approaches its absolute minimum. That point is 0 Kelvin, negative 273.15 degrees Celsius, negative 459.67 degrees Fahrenheit, absolute zero. But here, as we approach this floor, something important must be said carefully. At absolute zero, thermal motion, the random temperature-dependent vibration we have been discussing all night, would reach its minimum possible state, but it would not become zero. The laws of quantum mechanics, specifically the uncertainty principle, first described by Werner Heisenberg in the 1920s, tell us that particles cannot simultaneously have a perfectly defined position and zero momentum. Even at the absolute floor, a residual vibration called zero-point motion persists. It cannot be removed. It is not thermal energy in the ordinary sense. It is a fundamental quantum mechanical property of matter itself. So, absolute zero is not the temperature at which all motion stops. It is the temperature at which all thermal motion reaches its minimum. Even at the floor, the universe hums in a register too deep and too quiet for any thermometer to record. The concept was first approached theoretically in the late 18th and early 19th centuries. The French physicist Guillaume Amonton noticed as early as 1702 that the pressure of a fixed amount of gas decreased proportionally as it cooled, and extrapolated that at some sufficiently low temperature the pressure would reach zero. His extrapolation suggested a temperature around negative 270 degrees Celsius, remarkably close to the correct value determined centuries later. The more formal theoretical framework was developed by a series of physicists including Sadi Carnot, Rudolf Clausius, and William Thomson, later known as Lord Kelvin, whose name the absolute temperature scale now bears. What emerged from their work was not merely a lower limit on temperature, but a profound understanding of why that limit exists and why it can never be reached. The reason absolute zero is unreachable is not a limitation of technology. It is a consequence of the third law of thermodynamics, which states that as the temperature of a system approaches absolute zero, the amount of work required to remove any further heat from it approaches infinity. You can always extract some heat from a cold system, but doing so requires doing work. And as the system gets colder, extracting the next small amount of heat requires progressively more work. The approach to absolute zero is asymptotic. You can get closer and closer, but each step demands more effort than the last. This is not a temporary barrier waiting to be overcome by better refrigerators. It is a mathematical boundary embedded in the structure of thermodynamics, a boundary the universe has built into its own rules. And yet the pursuit of temperatures approaching absolute zero has been one of the most productive areas of physics in the past century and a half. Not because reaching the floor is the goal, but because the physical phenomena that emerge as you approach it are among the strangest and most beautiful that nature produces. The race to achieve lower and lower temperatures began seriously in the late 19th century. Oxygen was liquefied in the year 1877 by Louis Cailletet in France and Raoul Pictet in Switzerland, working independently and announcing their results within days of each other. Hydrogen was liquefied in the year 1898 by James Dewar, and the liquefaction of helium, which has the lowest boiling point of any element at 4.2 Kelvin, was achieved in the year 1908 by the Dutch physicist Heike Kamerlingh Onnes at Leiden University. This achievement opened the door to a new regime of physics where materials begin exhibiting behaviors that classical physics cannot explain. Kamerlingh Onnes put his new capability to use immediately. In the year 1911, cooling mercury to approximately 4.2 Kelvin, he discovered that its electrical resistance vanished entirely. Not diminished, vanished. The mercury conducted electricity with perfect efficiency, losing no energy to resistance, carrying current indefinitely. He called this phenomenon superconductivity. He received the Nobel Prize in Physics in the year 1913. Superconductivity was the first of a long series of extraordinary phenomena emerging near absolute zero. At approximately 2.17 Kelvin, liquid helium undergoes a transition to a state called a superfluid, in which it flows with zero viscosity. A superfluid has no internal friction. It flows through the tiniest openings, climbs up the walls of its container, and flows out over the rim, if not covered, and forms thin films that carry heat almost perfectly. And then there is the state of matter that sits most strikingly at the intersection of quantum mechanics and extreme cold. In the years 1924 and 1925, the Indian physicist Satyendra Nath Bose and Albert Einstein predicted, theoretically, that at sufficiently low temperatures, a collection of certain types of particles would all fall into the same quantum state simultaneously, losing their individual identities and behaving as a single collective entity. This state was called a Bose-Einstein condensate. The prediction was made in the 1920s. It was not confirmed experimentally until the year 1995, when Eric Coronal and Carl Wieman at the University of Colorado and Wolfgang Ketterle at the Massachusetts Institute of Technology independently created Bose-Einstein condensates by cooling gases of rubidium and sodium atoms to temperatures of a few hundred billionths of a Kelvin, above absolute zero. Coronal, Wieman, and Ketterle received the Nobel Prize in Physics in the year 2001. In a Bose-Einstein condensate, the quantum mechanical wave functions of individual atoms overlap and merge, and the entire collection behaves as a single quantum object with properties visible at the scale of ordinary laboratory observation. It is one of the most controlled and precisely understood states of matter that physics has produced. Now, consider where we must go to find these phenomena in the natural universe. Most of deep space sits at approximately 2.7 Kelvin on average. Set by the cosmic microwave background, there are rare natural exceptions. The Boomerang Nebula, a young planetary nebula approximately 5,000 light-years from Earth, has been measured at temperatures of approximately 1 Kelvin, colder than the cosmic microwave background itself. This occurs because gas expanding rapidly outward from the central star cools through a process called adiabatic expansion, losing heat faster than it receives energy from the surrounding radiation field. The Boomerang Nebula is, as far as current measurements show, among the coldest naturally occurring places known in the universe. But the coldest places that exist are not natural at all. They are in human laboratories. The current record belongs to a team at the Massachusetts Institute of Technology who, in the year 2021, cooled a gas of sodium atoms to approximately 38 picokelvin. 38 picokelvin is 38 trillionths of a degree above absolute zero. It is approximately 100 million times colder than the average background temperature of outer space. In a laboratory in Cambridge, Massachusetts, physicists created conditions colder than anything found naturally in the observable universe, in a volume smaller than a marble. For a fraction of a second, the universe made the floor. Humans are the ones reaching toward it, not to touch it. The third law tells us that is impossible and always will be, but to see what lies just above it. In the regime where quantum mechanics dominates and matter reveals behaviors, it hides at every other temperature. Cold, pursued to its extreme, does not reveal emptiness. It reveals structure. The closer you get to the floor, the more clearly you see the quantum mechanical architecture that underlies all matter at every temperature but normally hides beneath the thermal noise of ordinary warmth. Warmth is the noise that covers the deeper music. Absolute zero is where the noise finally goes quiet enough to hear what was always there. You cannot reach it. No one can, but you can get close enough to listen. And what you find when you listen, at 38 trillionths of a degree above the floor, is not emptiness. It is the universe, still humming, in the only voice it has left when everything else has been taken away. Let that image carry you gently forward, because the direction heat flows, from hot to cold and never spontaneously the other way, is not merely a fact about temperature. It is one of the deepest facts in physics about why the universe has a past and a future at all, and why you experience time moving in one direction rather than the other. We go there next, into the connection between the coffee cooling in a cup and the arrow of time itself. Put a cup of hot coffee on a table and walk away. You already know what will happen. Come back in an hour and the coffee will be cooler. Come back in several hours and it will be room temperature. Come back tomorrow and it will still be room temperature. Not warmer, not hotter than when you left it. not having somehow drawn warmth from the cooler air around it and concentrated it back into the cup. The coffee cools. It does not spontaneously reheat. This process does not reverse. You have known this your entire life, and it has probably never once struck you as remarkable. It should. Here is the thing that makes this observation one of the most profound puzzles in physics. The laws that govern the motion of individual particles are time-symmetric. If you filmed a single collision between two atoms and played the film backward, the reversed collision would be perfectly valid physics. There is no way, looking at the collision itself, to tell which direction time is running. The particle equations do not distinguish between past and future. And yet, at the scale of cups of coffee and rooms full of air, time has a direction that is unmistakable. The coffee cools. Heat flows from hot to cold. Processes that are perfectly legal at the particle level never occur at the everyday level. Something creates a direction to time that the underlying equations of motion do not contain. That something is entropy. Entropy is one of the most important concepts in physics and one of the most consistently misunderstood. A more precise description than simply disorder is this. Entropy measures the number of different microscopic arrangements of a system that would produce the same macroscopic appearance. Consider a simple picture. Take a box divided in half by a partition. On one side, 100 molecules of gas. On the other side, nothing. Remove the partition. The gas expands to fill the whole box. Now it is possible, in principle, for all 100 molecules to wander back to their original half by chance. Nothing in the laws of particle motion prevents this. Each molecule moves randomly. It could, at any moment, be in either half. But the probability of all 100 molecules simultaneously being in the same half is approximately 1 in 2 to the power of 100. 2 to the power of 100 is approximately 1, followed by 30 zeros. If the molecules rearrange themselves randomly 1 billion times per second, the expected waiting time for all of them to end up in the same half again would still be astronomically longer than the age of the universe. This is entropy. Not that the reverse process is forbidden by any law. It is that the reverse process is so fantastically improbable that it never occurs in practice. The system moves toward the arrangement with the most alternatives, the highest entropy, simply because that is overwhelmingly the most likely outcome at every step. The second law of thermodynamics states that the total entropy of an isolated system never decreases over time. Entropy increases continuously. The coffee cools. Order becomes disorder. Concentrated energy becomes diffuse. And the direction of this process defines the direction of time itself. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past and not the future because our memories are records of lower entropy states that have evolved into higher entropy states. That chain defines what we call the arrow of time, the sense in which time moves from past to future rather than future to past. But this raises an immediate and critical question. If entropy always increases, where did the low entropy come from in the first place? The universe today has high entropy compared to the universe of 1 billion years ago, but it has low entropy compared to the universe of 1 trillion years from now. Entropy has been increasing throughout cosmic history, which means, at the beginning, it must have been very low, extraordinarily low. The Big Bang, must have begun the universe in a state of remarkably low entropy. The physicist Roger Penrose of Oxford University has written extensively on this point, arguing, according to his analysis, that the initial low entropy of the universe is one of the most profound facts about physical reality, a constraint so specific that explaining it may require physics beyond anything currently understood. The low entropy beginning is not something that follows automatically from the Big Bang. It is an additional condition, a specific choice of initial state, that distinguishes the universe we inhabit from the much larger space of possible universes that the equations of physics would permit. What does all of this have to do with the sun being hot and space being cold? Everything. The sun is hot because it is burning hydrogen, converting mass to energy through nuclear fusion, releasing energy that was locked into the structure of hydrogen nuclei at the beginning of the universe. That energy is the low entropy inheritance of the Big Bang. The sun is spending it, converting low entropy concentrated nuclear energy into high entropy diffuse radiation, spreading in all directions across space. Every photon that leaves the sun and spreads into the cold void is entropy increasing, concentrated energy becoming diffuse, the universe moving, as it always moves, from lower entropy toward higher entropy. Earth intercepts a tiny fraction of this radiation and temporarily concentrates it into local structures of lower entropy. Living organisms, weather systems, ocean currents. Life on Earth is not a violation of the second law of thermodynamics. It is a local, temporary decrease in entropy driven by the much larger entropy increase of the sun, spreading its energy across space. The net entropy of the system, sun plus Earth plus space, increases continuously. Life is what happens in the corner of the room where the energy gradient is steep enough to support it. The sun is hot and space is cold. And that difference, that gradient, is what makes it possible for any organized process to occur at all. A universe of uniform temperature, at thermal equilibrium, would be a universe where entropy had reached its maximum and no further change was possible. No gradients, no flows, no weather, no oceans, no chemistry, no biology, just uniformity, forever. The heat death of the universe is the name given to this eventual state. First proposed in its modern form by Hermann von Helmholtz in the year 1854. In the very far future, if the universe continues to expand and cool as current physics predicts, all stars will have exhausted their fuel. Black holes will have evaporated through the slow process of Hawking radiation. The temperature everywhere will approach the temperature of the background radiation, which will itself have cooled further through the continuing expansion of space. There will be no gradients, no flows, no work that can be done. The physicist Freeman Dyson explored these questions in a paper titled Time Without End, published in the journal Reviews of Modern Physics in the year 1979. Dyson asked whether any form of organized information processing could survive indefinitely in a cooling universe. He proposed, with characteristic optimism, that intelligence might in principle adapt to ever lower temperatures and slower processes, performing the same total amount of computation by thinking more slowly as the universe cooled, spending exponentially less energy per thought while extending its existence across an ever longer time. The question remains genuinely open and debated among physicists and philosophers. What is clear is that the endpoint is a universe far colder and far more uniform than the one we inhabit. However, the details of that distant transition ultimately resolve. But this endpoint is so remote in time that the numbers involved require patience to absorb. The current age of the universe is approximately 13.8 billion years. The last stars are expected to exhaust their fuel in somewhere between 100 trillion and 1,000 trillion years. The evaporation of the largest black holes through Hawking radiation is expected to take on the order of 10 to the power of 100 years. These timescales make the current age of the universe look like the first fraction of a second of a day that lasts longer than the universe has existed. We are, in cosmic terms, at the very beginning. The stars are still burning. The gradients are still steep. The arrow of time is still pointing clearly from past to future. And in the vast distance between the entropy of now and the entropy of the ultimate equilibrium, everything we know exists. Every star and planet, every ocean and mountain, every living thing, every thought and memory and moment of warmth felt on a cold day, all of it powered by the distance between the low entropy beginning and the high entropy end, playing out slowly across a timescale so enormous that even the longest human civilization would be invisible within it. There is a line in this that deserves to rest in you before we continue. You are alive because the universe has not yet finished cooling down from the Big Bang. That is not a metaphor. It is thermodynamics. The warmth that keeps you alive tonight, the warmth of your body, of the room, of the planet, is the temporary local consequence of a universe still spending the low entropy inheritance it was given at the beginning of time. Every heartbeat is entropy increasing somewhere. Every breath, every thought, every moment of feeling warm in a cold world is the universe moving in the only direction it is permitted to move. Forward, toward equilibrium, toward the quiet, but not yet. Not for an incomprehensibly long time yet. Rest in that. The universe has given us an enormous amount of time in the gradient between its hot beginning and its cold eventual end. We are using some of it right now. Lying in the warm, wondering about the cold outside the window and the colder still beyond the atmosphere. That wondering is itself a consequence of entropy. A low entropy mind in a high entropy universe. Temporarily organized enough to ask where all of this is going. The answer is slowly, beautifully, irreversibly, toward the quiet, but not tonight. There is a particular quality to warmth that you only fully appreciate in contrast to cold. Not the cold of a winter morning. Though that has its own instructive quality, the cold we have been exploring tonight, the cold of interstellar space and the deep floor of absolute zero and the long, slow drift toward thermal equilibrium, is not the kind of cold that makes you reach for a sweater. It is the kind of cold that makes you understand, perhaps for the first time, what warmth actually is, and what it means that you have it. You are warm right now, not because warmth is the default state of the universe. You now know that it is not the default state of the universe. The average background temperature of deep space is approximately 2.7 Kelvin on average. The equilibrium toward which all isolated systems tend is thermal uniformity, the same temperature everywhere, which, in the ultimate case of the universe as a whole, means a temperature approaching absolute zero as the last stars exhaust their fuel and fade. your warmth, the 37 degrees Celsius of your body, the 15 degrees of the atmosphere around you. The warmth of the planet maintained by the greenhouse effect and the steady output of the sun is not the default. It is the exception. It is a local, temporary, precisely maintained departure from the cold that would prevail in the absence of the sun, in the absence of the atmosphere, in the absence of the chemical processes running continuously in every cell of your body. You are a warm thing in a cold universe. Consider the chain of conditions required for this moment to exist. A star had to form from collapsing gas and ignite nuclear fusion, providing a continuous source of electromagnetic radiation for billions of years. Stars like the Sun, stable enough to burn steadily for the billions of years required for complex life to develop on a nearby planet, represent a specific subset of all possible stars, those in the right mass range, composed of the right mix of elements, formed in the right conditions. A planet had to form at the right distance from that star, close enough to receive sufficient energy to maintain liquid water at the surface, far enough not to be locked in the kind of runaway greenhouse effect that consumed Venus. The range of distances satisfying both constraints is not infinitely narrow, but neither is it wide. An atmosphere had to develop of the right composition, enough greenhouse gases to provide the 33 degrees of warming that keeps the oceans liquid. Not so much that the warming runs away. The current composition of Earth's atmosphere is the result of 4 billion years of geological and biological regulation. A slow feedback between rock chemistry and living organisms that has maintained habitable conditions through enormous changes in solar output and geological upheaval. And within that carefully maintained planetary environment, chemistry had to organize itself into self-replicating structures. Those structures had to develop the capacity to harvest energy from their environment, to maintain their own internal temperatures, to reproduce and evolve. The origin of life remains one of the deepest unsolved problems in science. We know it happened on Earth approximately 3.8 billion years ago. We do not know with certainty how readily it occurs given the right conditions. And researchers who study this question openly acknowledge the genuine uncertainty. The physicist Erwin Schrödinger, writing in his remarkable book, What is Life, in the year 1944, proposed that living organisms are distinguished by their ability to extract what he called negative entropy from their environment, meaning organized, low entropy energy, and use it to maintain their own internal structure against the relentless tendency toward disorder. In Schrödinger's framing, life is what matter does when it finds a way to temporarily resist the drift toward equilibrium by continuously consuming order from its surroundings. The insight has been refined and extended in the decades since, but the core observation holds. Life is what organized matter does when it finds a steep enough gradient and is clever enough to exploit it. You are exactly that, an organized system exploiting a gradient. Every calorie of food you have ever eaten is solar energy that has passed through a chain of transformations. The plants that produce the food absorbed solar radiation through photosynthesis and stored it as chemical energy in sugars and starches. The animals that ate the plants transferred that stored energy up the food chain. When your body metabolizes food, it releases energy that entered the biosphere as sunlight, was captured by photosynthesis, stored in chemical bonds, transferred through the food web, and is now powering your heartbeat and warming your skin. The chain from the nuclear fusion in the sun's core to the warmth of your body right now is direct and traceable. In a very literal sense, you are made of sunlight. Let that land for a moment before we continue. The energy that maintains your body temperature right now. The energy powering every thought you are having. The energy that will sustain your breathing through the night. It is solar energy, captured by plants, stored in chemical bonds, and arriving in you through the food you have eaten. The sun made it. The plants caught it. Your body is spending it. You are made of sunlight and the cold of space. The cold we have spent this night exploring is not separate from this story. It is the context that makes the story possible. Life requires energy gradients. A gradient is a difference. A region of higher energy adjacent to a region of lower energy, which allows energy to flow from one to the other and do work in the process. The steeper the gradient, the more work is possible. The sun at nearly 6,000 Kelvin, surrounded by space at approximately 2.7 Kelvin, on average represents one of the steepest energy gradients accessible to life on Earth. The difference between those two temperatures is the engine that drives everything. If space were warm, nearly as warm as the sun, that gradient would nearly vanish. There would be nowhere for the sun's energy to go. No flow from hot to cold. No work to be done. No weather. No photosynthesis. No metabolism. No life. The cold of space is not an obstacle to life. It is one of the conditions that makes life possible. It is the cold side of the engine, and without it, the engine cannot run. You are alive because the universe is cold. Let that settle, not as a frightening thought, as a true one. The sun has been burning for 4.6 billion years, steadily converting hydrogen to helium in its core, steadily releasing energy as radiation, steadily maintaining the warmth gradient between itself and the cold of space that makes this planet habitable. It will burn for approximately another 5 billion years before exhausting its hydrogen fuel and expanding into a red giant. 5 billion years is a number so large it means almost nothing to human intuition. The entire history of complex life on Earth spans about 600 million years. Human civilization, in any recognizable form, is perhaps 10,000 years old. 5 billion years contains 1,000 times the entire history of complex life, 10,000 times the entire history of human civilization. We are early, not just early in the history of the sun, which is roughly middle-aged, early in the history of the universe, which is 13.8 billion years old, but has on the order of 100 trillion years of star burning ahead of it before the last stars exhaust their fuel. We exist in the first fraction of the cosmic timeline, during which stars like the sun burn and planets like Earth maintain warm surfaces and life of the kind we know is possible. The cold that surrounds us. The approximately 2.7 Kelvin of the cosmic background on average. The near absolute zero of interstellar space. The gradient between that cold and the warmth of our star is not a temporary condition that will soon change. It is the condition of a universe still very early in its thermodynamic evolution, still burning through the low entropy inheritance of the Big Bang, still maintaining the gradients that make chemistry and biology and consciousness possible. You are alive in the part of the universe's history when the gradients are steep, when the stars are burning, when the cold of space and the heat of stars create the conditions for organized complexity to exist. The cold teaches us this. not as an abstract lesson, but as a physical reality that your body navigates every moment. Every breath you take is a negotiation with entropy. Every heartbeat is a temporary local arrangement maintained against the tendency of warm things to cool. Every thought is a pattern sustained against the thermal noise that would dissolve it if your metabolism ceased. You are not separate from the thermodynamics. You are a consequence of it, a local arrangement of organized complexity in a universe drifting toward equilibrium, powered by the gradient between a star and the cold, sustained by the precise conditions of distance and atmosphere and chemistry that happen to exist on this particular planet at this particular moment. The cold of space is vast and real and will, in the end, prevail. Every star will go dark. Every gradient will flatten. The universe will reach its quiet, cold equilibrium and remain there for a period of time so long that the current age of the universe is to it, as a single atom is to the visible cosmos. But not now, not for an incomprehensibly long time. Right now, the sun is burning. Right now, the gradient is steep. Right now, the atmosphere is holding the warmth in and the cold out, at exactly the level to keep the oceans liquid and the air breathable, and the temperature of this planet in the range where the organized complexity we call life is not merely possible, but flourishing. Right now, you are warm, in a universe that is almost entirely cold, almost entirely empty, almost entirely silent. You are a warm, organized, conscious thing, briefly present in the gradient between a star and the void, aware enough to wonder about it. That is not a small thing. It is, as far as we currently know, one of the rarest things the universe produces. You have traveled a very long way tonight without moving at all, which is fitting. When you think about it, that was the lesson all along. There is nothing more you need to hold on to now. The numbers have done their work. The ideas have settled wherever they will settle. If the details are already blurring as you sink deeper into the pillow, let them blur. That was always the plan. Facts fade. The feeling can stay. So as your breathing slows, keep only the pictures. A child in a backyard on a summer afternoon, squinting up at the sun, asking the most reasonable question in the world. Why is space cold when the sun is so hot? And the answer, taking an entire night to unfold, as the best answers do. Not ending the question, but deepening it, until the question itself becomes a kind of home. A metal spoon in hot soup, molecules passing their motion hand to hand through solid matter, the most intimate process in physics, happening in kitchens everywhere, every day. Unremarkable and extraordinary in equal measure. An astronaut floating outside a hatch with one side blazing at 250 degrees and one side frozen at negative 250 degrees. The whole universe demonstrating its rules on one small human form. In silence, above the blue curve of the Earth. A large horn-shaped antenna in a field in New Jersey in the 1960s, pointed at the sky, finding a signal that no amount of careful checking could remove. Two scientists, who had spent months trying to eliminate an unwanted noise, discovering that what they had found was not interference at all. It was the oldest light in the universe, still ringing, 13.8 billion years later, in every direction at once. A spacecraft the size of a small car, launched in the year 1977, carrying a golden record with the sound of wind and rain and bird song, and a mother speaking to her child, crossing the boundary of the solar system and entering the interstellar cold, still transmitting, still going, moving through a region of space where the dominant temperature is set not by any star, but by the ancient light of the Big Bang. We sent something into the deep cold, and it is still going. A laboratory in Cambridge, Massachusetts, where physicists cooled a gas of sodium atoms to 38 trillionths of a degree above absolute zero, colder than anything the universe produces naturally. A small volume of matter more still than the void between galaxies, created deliberately, held for a fraction of a second, listening to the music that warmth normally covers, and the approximately 2.7 Kelvin on average, passing through your walls right now, through your body, through everything around you, as it has been doing since before the Earth existed, since before the Sun existed, since before the first star lit anywhere in the darkness. Ancient photons from the clearing of the cosmic fog, still traveling, still carrying the record of what the universe looked like when it was 380,000 years old and the light was finally set free. These things are all happening simultaneously. Right now, while you lie here, the photons crossing from the sun, the spacecraft crossing the interstellar medium, the ancient light passing through everything, the corona burning above the quiet surface, its million-degree secret still not fully told, the cold of space holding the same temperature it has held since long before the Earth existed. The universe does not pause for us. It continues its long, slow drift from the hot beginning toward the cold equilibrium, spending the low entropy inheritance of the Big Bang in stars and gradients and brief, local, organized complexities like the one you are right now. You are one of those brief, local, organized complexities. Varm, temporarily, conscious, briefly, wondering, which may be the most extraordinary thing that matter has yet learned to do in the 13.8 billion years since the light was first set free. The question the child asked in the backyard turns out not to have a simple answer. It has a deep one, a beautiful one, an answer that passes through the nature of heat and the three ways it travels, through the inverse square law and the near emptiness of space, through the ancient light of the Big Bang and the arrow of entropy and the necessary role of cold in making warmth meaningful. The sun is hot because the universe started low in entropy and is spending that inheritance through nuclear fire. Space is cold because that inheritance is being spread across a volume too vast for any single star to warm. And you are warm because you exist in the gradient between the two, at exactly the right distance from exactly the right star, wrapped in exactly the right atmosphere, powered by the sunlight captured by the plants. That became your food, that became your breath. That breath is slowing now, quietly, as thoughts dissolve. The cold is not the enemy of the warmth you feel tonight. It is the condition of it. Without the cold, there would be no gradient. Without the gradient, there would be no flow. Without the flow, there would be no work. Without the work, there would be nothing asking questions in the dark, nothing wondering about stars, nothing warm enough and organized enough to lie still and feel the weight of the universe and find it, against all odds, beautiful. The sun knows the space is cold. It burns anyway. The universe knows it is drifting toward equilibrium. It maintains its gradients anyway. For now, for the incomprehensibly long time that the remaining fuel allows, and you, warm thing in a cold universe, conscious, briefly, in the middle of the long arc from hot to cold, can know all of this and still feel the warmth of the blanket and the weight of the pillow and the slowing of the breath that means the day is done. The stars are keeping their distances tonight. The cold is staying where it belongs, on the other side of the atmosphere, on the other side of the glass. The sun is on the other side of the planet right now, warming other rooms, other windows, other people lying in the dark, wondering about the same sky. Everything is in its place. The gradient holds, the warmth remains, and the only journey left tonight is the small, familiar one from here to sleep, which your body knows the way without being told, which requires no physics and no understanding, only the willingness to let go of the thinking and trust the warmth to do what warmth has always done. Hold you through the cold, through the dark, until the sun comes back around. Good night. Rest well, under the warmest sky this cold universe has ever managed to make.